Okay, bombs away.
Oh, lovely. Well, thank you so much for joining us, everyone. This is really exciting to have you all here, and those of you who are calling in and those of you who will be watching the recording. We're really pleased. It's my honor and my pleasure to be here with Mark Hillary, who was my thesis advisor. And we found each other by coincidence and a happy accident. And I was originally a student here at the Graduate Center, but in the math department, and I wanted to write quantum algorithms to help with my dissertation. And so I was told, you must find a physicist. And by happy chance, I found Mark Hillary. So I'm proud to say I'm Hillary number one. And so when I decided to leave academia and come over to Sandbox AQ, it was a huge leap for me. I had been an academic for more than 20 years, a researcher, a professor, a committee member, and all the things that you all do. But it was really a moment for me to think through, how can I make a larger impact? And can I still be in the education space and still promote all of the education that I love and work with the students that I love so much? How could I do this maybe coming from outside the academic setting? And so I was really, really thrilled to have the opportunity to work with Sandbox AQ, AI, quantum. And so I'm here with Mark Hillary, and we decided to when I first started, support quantum education from within CUNY to catalyze collaboration across the campuses. CUNY has 24 campuses, 275,000 students, and quantum education at CUNY is scattered. There are pockets of folks doing things who don't necessarily talk to each other. So we wanted to try to work on that together. And we also wanted to loop in others in the quantum community, such as NYU. So we have the chair of applied physics, Sean DiBartolo, here with us from NYU, who is our close partner and collaborator. With him, we're creating a quantum technologies quantum engineering minor at the engineering school of NYU. And we're also hoping to loop in other partners. So I'll let Mark say a few words about his work here with the CUNY ITS, and then I'll give you a 1-minute welcome from Sandbox, and then we'll pass it over to our wonderful speaker.
Okay. Well, thank you, Mariana. I guess I should stand here
Yeah.
because of the microphone. Yeah, this is, I think, the third workshop that I have organized for ITS. It is the first one in person, that made it kind of scary. When it was all virtual, there was some expert taking care of everything, and I just didn't have to do much. This one, I have to order food and all this other interesting stuff, and I have a huge amount of help from both Vadim and John Tarillis. I want to thank both of you for that. And yeah, we teach courses, and we teach a graduate course at the Graduate Center in Quantum Information, and Seth Cottrell has developed a course, an undergraduate course at City College. He's also developing a lab to go with it for quantum information. So really trying to promote quantum information here at the City University of New York. And I would really like to thank both Sandbox and also the Simons Foundation for their support of these efforts. So I'll turn it back to you, Mariana.
Wonderful. Thank you so much, Mark. So a real quick intro to Sandbox, because I'm sure you're wondering, well, what is Sandbox? So we are a SaaS company, and we spun out of Alphabet X, Google X, Alphabet X. And so I'll show you the slide where we have a little bit of our story, but really we are focusing on using quantum technologies. We don't build quantum hardware for processing. So I put that right out. When you think of a quantum company, you immediately think, oh, they're building a quantum computer. We do not build quantum computers. We use quantum particles as sensors, not as processors for right now, but we also are in the quantum security space. And we also are looking at quantum-inspired classical techniques, which can really speed up computation for the purposes of drug discovery. So a little bit more about our story. As I mentioned, we started from within Alphabet, and this started about 2016. Our CEO, Jack Hidary, he got a group of really bright and curious minds around him to start looking at some projects related to quantum technologies. And then he wrote a book in 2019, Quantum Computing: An Applied Approach, which is really, really quite good. It has all the linear algebra in there. You need to get up to speed. I recommend it, especially for folks who perhaps are in computer science or electrical engineering or mathematics or another field who are looking, you know, for an entry point. It's a really great entry point. And Eric Schmidt was so excited about what was happening with this little pocket of engineers that in 2020, he decided to become the chair, to join Sandbox, and he is the chair of Sandbox right now. Eric Schmidt, you might know him as CEO of Google, CEO of Alphabet for many years. We have amazing results, publications, one which was more recent in Nature about transitioning over to quantum resistant cryptography. I'm going quickly because Max will say a little bit more about this at his talk. Max Ruff is one of our amazing engineers. He did his doctoral work in quantum networks. He'll be presenting as well this morning. So here really are three main verticals, but education underlies all of it. We work with all the verticals, our education team, and it's really forward thinking because it's really clever thinking and essential thinking, because the technologies that we're developing are so rapidly changing that we constantly have to upskill at Sandbox. Any information we know, any skills we have, in 3 years will be stale unless we're constantly working to educate ourselves and constantly evolve as the technology evolves. So education, they recognized, Jack recognized, was an essential component of this company. We all have learning plans. We have this, we foster this culture of growth and of learning. Even our CEO has a learning plan. We're all taking courses, we're all reading papers, we're all teaching each other and learning from each other. Here are the verticals: simulation and optimization, quantum security and communications, quantum sensing. On the security and communications front, we have strategic investments. So QNect is one of them. They're out of the Brooklyn Navy Yard. They're our neighbors. CEO was actually one of the students at NYU Tandon with myself and with John many years ago. She's amazing. Her name is Noelle Goddard. She also taught at Hunter with Mark. Again, the quantum world is small. We also invested in another company, which is in Canada, for QKD. So we have strategic investments here. Let me move along. We have a brain trust. Here's our education team. We're a small but mighty team. And this is how we work together. So we work on corporate and federal technical trainings. So we create courses for folks who are stakeholders and decision makers in the federal government. We make courses for C-suite of our customers who want to upskill on quantum tech and AI. We work to develop university, high school, middle school curriculum. I told you about the effort with NYU for the minor degree program in quantum engineering. We have a YouTube channel, so we do general education. We put things out into the open. And we have a residency program, which some of you might be interested in. It's with interns and also postdocs. And then we do partnerships like this one. That's why we're here today. So I'm just going to flash the slide with the residency program and just tell you, if you're interested, just go to our website. We have our open positions posted. They get updated very, very often. If you don't see a position that is quite right for you, reach out to us. Happy to chat about it. We'll have your resume. And then if a position opens up that we think you might be a nice match for, we'll reach out to you. So thank you so much. We're so thrilled to be here. And without further ado, we pass it over to our very first speaker. Okay, so I need to stop sharing and I'll let our speaker share. Thank you so much for your attention, everyone. Thank you, please.
Maybe.
Okay. Can all the attendees online see my screen? Okay. Okay, great. Yeah. Thank you. It's really a great pleasure to be here, and I would like to thank the organizers, and in particular Mark, for inviting me to talk about some of our recent work. So actually, I was telling Mark, I was reading his papers even like 20 years ago when I was an undergraduate student, and these are very inspiring quantum cryptography papers. And now we finally have a chance to see each other in person, and also it's a great pleasure to see all the audience here. So today, what I'm going to talk about is using entanglement to enhance the performance of a network or array of sensors, and then we further build on this concept to develop entanglement enhanced data processing units. So before I really get into entanglement-based technologies, so let's first do a quick overview on what now people call the first quantum revolution, which was really sparked by the formulation of quantum mechanics in the early 20th century. So there we had pioneers, including Paul Dirac, Einstein, Schrödinger. They jointly laid the foundation of this theory, and then which led to quantum devices, or the first generation of quantum devices. And these devices operate at a microscopic level. They obey the laws of quantum mechanics. They include transistors, lasers, and some imaging capabilities. And then we further put all these together, they give rise to our current internet or the information age. So now we have billions of devices all connected across the internet to empower a wide range of applications. Okay, but although the information technology is still quickly developing, so now the scientific community has already envisioned what we call the second quantum revolution, and this is indeed a new discipline enabled by the combination of quantum mechanics and the information, and at the core of the second quantum revolution, or sometimes we say it is enabled by quantum information science. The core of this technology is a fundamentally new resource called entanglement. So entanglement was first proposed or discovered by Einstein and with two of his colleagues in the early 20th century. So initially, Einstein wanted to use it to actually refute some of the foundations of quantum mechanics, but then as more experimental evidences were accumulated, so now we believe entanglement is actually real. It is just basically how nature behaves at a microscopic level. So it basically nature exhibits both the non-local and some really strong correlations with entanglement. And the last year's Nobel Prize was awarded to three pioneers who studied the fundamentals of entanglement to verify entanglement, and also to demonstrate some of the proof of concept entanglement-based technologies. So now we are really on the verge of leveraging entanglement to further advance science and technology to enable capabilities that are out of the reach of classical technologies. So now let me just give you a quick snapshot on how entanglement is produced and what is entanglement. So actually in our lab now it actually became a quite routine technique in a quantum optics lab to generate entanglement. So actually the process is pretty simple. So you take a piece of nonlinear material, typically a nonlinear crystal, lithium niobate or KTP, and you eliminate the crystal with a flux of higher energy photons, which we call pump. And because of the nonlinearity of the crystal, at a small probability, a pump photon is going to split into a pair of photons, which we call, sometimes we refer to them as a signal and the idler. Okay, so in this process, you can actually see that the two photons are almost emitted at very close times from the same hump photon. So if you, in the experiment, if you count the arrival times of both photons, you observe that the correlation is actually very tight. Okay, so this is what people call coincidence counts. But on the other hand, due to energy conservation, if one photon carries more energy and the other photon must carry less energy. So here, if one photon is like more blue, the other photon must be more red, and vice versa. Okay, so if one photon would carry less energy, or more like blue shifted, red shifted, and the other photon must be more blue shifted. And according to this very simple relation in quantum mechanics, there's a very close connection between energy and frequency. So just by showing this very simple cartoon, you observe that the two correlations actually simultaneously shared by the two photons. So first, they are anti-correlated in frequency, and they are highly correlated in time. Okay, but now if you think about both correlations, and you find that this is non-classical, because in the classical domain, so you can actually make two photons highly correlated in time, or they share a very tight temporal correlation. You can create two very narrow pulses and overlap them. But then if you look into the frequency domain by taking a Fourier transform, you see the spectrum of both photons are very broad. And if you measure the color of either photon, it's going to be very uncertain, so they do not actually share any spectral correlation. And vice versa, you can make their colors completely overlap, which means both photons are very narrow in frequency, and because it's very narrow, it's like a monochromatic field. And then in the time domain, it's almost like a CW wave, so you can never predict when the photon is going to come in. So they do not share any temporal correlation. So in the previous case, as I showed, the two photons share both frequency anti-correlation, and the correlation in time is a non-classical feature. So and this is what shows the non-classical correlation, and what we call it is entanglement. So now you can take advantage of that by, for example, using one photon as the probe, and the other photon as the reference to develop sensors that are more precise than classical sensors. So here, just give you a very recent example that we demonstrated in the lab, what we call quantum enhanced or entanglement enhanced covert sensing. So this is the configuration. So in classical covert sensing, what you do is that you use a laser to generate a pulse, and this pulse will be used to interrogate this target, and there's some return at the receiver. So actually a very small amount of signal is reflected back to the receiver, but it is embedded in this very bright noise background. Okay, and the receiver attempts to take a measurement to infer the properties, the physical properties of the object. And at the same time, there's a opponent, Willy, and we assume that the opponent can collect basically the scattered the power from the environment, and from the power that Willy collects, he tries to infer the sensing attempt. So he wants to know if anyone is actually sending the signal. And in the quantum case, so now you have a entanglement transmitter, okay, and the entanglement transmitter would generate entangled probe and the local reference. And when the probe gets back to the receiver, as you see, there's a bright noise background, but as compared to the classical case, now you have a locally returned reference, which would allow you to construct a quantum receiver that performs a joint measurement on both the returned probe and the locally returned reference to infer the physical properties of the target of interest. Okay, and also this opponent tries to capture all the scattered photons that do not arrive at the receiver to infer the sensing attempt. So he wants to know if there's, the signal that he receives is actually above a certain level, so that he would be able to tell somebody is sending a probe signal. Okay, so then the entanglement transmitter would just be, in the previous slide, a nonlinear crystal pumped by higher energy pump photons to create entangled signal and idler photons. And you use idler, you return the idler at the transceiver, and you send the signal out to probe the target. Okay, but for the quantum receiver, it is actually a unconventional measurement apparatus. This is how it works. So that this is your received signal. So it is actually, embedded in this very bright noise background. So this is this tiny bit is from your original transmitter, and it actually share a phase conjugation relation with the idler field. So which means if this phase is positive, and the idler phase must be negative. Okay, and because of this, what we call phase conjugation, okay, you are not able to directly interfere them on a beam splitter. Okay, so but what you can do is that you use a low gain phase conjugator to generate a phase conjugate field, which basically flip the phase of the received signal. Okay, and also to reduce the noise of the background, and then the phase conjugate field will be able to interfere with the idler field on a 50-50 beam splitter, followed by two detectors to take a balanced measurement. Okay, so this is how our quantum receiver works, and then we took some measurement to quantify the quantum advantage. And as you see in the entanglement-based case, the error of estimating the phase of the object is actually reduced. And this is the gap quantifies the quantum advantage, and such a quantum advantage would sustain even in a very bright noise background. So this is what we demonstrated in this experiment, which was published last year. So this experiment actually allowed us to demonstrate this entanglement enhancement in sensing. Okay. At a single sensor, right? Because now the transmitter and the receiver are co-localized, okay, at the sensor. It's like a radar type of measurement regime, okay. But entanglement as a fundamentally new quantum resource also exhibits other features, and in particular non-local features, which means you can generate multi-party entanglement, and you can distribute multi-party entanglement to different locations, and regardless of the spacing between them, they still share this very tight correlation. And over the past years, we wanted to understand, are you able to leverage this non-local property of the entanglement to develop useful technologies? Okay. And actually, in the future, our vision is to create a quantum internet, and this infrastructure would allow us to distribute entanglement across multiple nodes. And now all the nodes would share entangled states, and then we want to further ask the question whether or not you can take advantage of the distributed entanglement to endow new capabilities to develop the next generation technologies. So then in the past few years, we have been studying this problem and put together a few experimental demonstrations. So this is what I'm going to tell you about in today's talk. So first, we put together a sensor network to detect radio frequency fields, and more recently to demonstrate entanglement enhanced optomechanical sensing, which you can use to detect force signals for initial navigation, and to enhance the performance of these ultra precise detectors for the searches of new physics. And then we further leverage the entangled sensor network to allow them to tackle some of the data processing problems. Okay. So now let's first talk about the entangled sensor networks. So actually sensor networks are ubiquitous, right? So for example, you think about your cell phone's camera, so it actually comprises millions of pixels, and if you consider each pixel as a standalone sensor, and actually these millions of sensors actually work collectively to address imaging problems. Okay, so so this is indeed a sensor array. Other scenarios include telescope arrays to detect, to image black holes, as recently demonstrated, and also in some of the military applications, phased array radars, to for target detection or target tracking. So now the benefit of a sensor network as compared to a single sensor can actually be easily quantified, right? So this is a classical case. So say now you have M sensors that work jointly to address measurement problems, and here they all probe the same target. So as we remember, we go to the physics lab and we carry out an experiment, and to make the measurement more precise, and you can take multiple measurements and to average out the measurement outcome, and that would actually allow you to reduce the statistical fluctuation. Okay, so here is the same idea. So you use M sensors, and each sensor would see the same signal power S, but they also have uncorrelated noise. But when you take the ensemble average of the data produced from all sensors, you can effectively increase the signal to noise ratio, okay, or reduce the statistical uncertainty. And the scaling is proportional to the number of sensors, okay, and it is actually linear. So as you adding more sensors, and the SNR would actually scale linearly, okay. So this is the classical case, but in the quantum case, the scaling would become slightly different. So now you also consider a network of M sensors, okay. You consider a network of M sensors, and each sensor sees signal power of S. How do you just leave this?
Make the bottom go away.
Yeah, how do I make the bottom go away?
There's a, if you go up to the top, view options. Yeah.
very
top, no, left, middle top, no, middle top.
Oh, yeah.
See, it says view option. Hide something, hide video tab. Yeah. Hide something. Full screen.
Oh, but that's fine. Oh, just don't see it. Maybe. Okay, that's fine.
Oh,
But,
actually, just click on the main part of it.
oh, okay. Yeah, now it works. Yeah, but just wanted to show you this. So now the noise actually becomes correlated due to entanglement shared by multiple sensors. Okay, so as a result, the SNR scaling actually changed from the linear scaling to a quadratic scaling in a ideal case. So this is indeed the enhancement enabled by entanglement, or having a entangled sensor network. Okay, so now the question is, this is all from theory, or you can derive the scaling from quantum measurement theory, but how do you actually put together a protocol that would actually demonstrate this quantum advantage? Okay, so this was actually a theory proposal by my theory collaborator Xintao Zhuang and my postdoc supervisor Jeff Shapiro and myself, published 5 years ago now. So the idea is to leverage squeeze light as a quantum optics resource to create entangled multi-party entangled state to serve a entangled quantum sensor network. Okay, so now you have ScreenSlide as a fundamentally new resource. And in case you're not familiar with ScreenSlide, ScreenSlide is a quantum state of light with one quadrature with more uncertainty at the cost of enlarging the uncertainty of the other quadrature. Actually, LIGO uses ScreenSlide now to enhance the performance of their gravitational wave detectors. So here, we just passed the ScreenSlide across multiple beam splitters to create entangled probes. And at each sensor node, we equipped it with a sensor, and I will explain what sensor it will be. Followed by a detector, and the data are jointly processed in a classical processor to infer the property, a physical property of the object being probed across all the sensors. So actually there are other works, theory works and experimental works from Alex Goshov's group and from other groups it's not completely the same setting. So some of the protocols use discrete variable single photon based states, but our protocol uses a continuous variable states. And also there are experiments from Ulrich Anderson's group and Jianwei Pen's group and Lim's group also published very recently. So we have studied so now two different scenarios of using the entangled sensor network to address practical sensing problems. But the key here is that at each sensor node, you introduce a transducer. Okay, so what the transducer does is that it would convert physical measurement, okay, from one domain to the optical domain. So for example, this is a force transducer or optomechanical transducer, which would probe the force signal that it sees and convert that into a modulation in the optical domain. Okay, so in doing so, you would take optical measurements to infer the original force signal, and at the same time, you can also benefit from the entanglement in the optical domain to enhance the measurement performance. So that's the idea. So we actually collaborated with Dow Wilson's group at the University of Arizona. So his group is experts of fabricating these optomechanical sensors. So this is you can think about this as a membrane, okay, or it's like a trampoline, okay, and the sensor responds to external force signals, and now when you shoot a light to the sensor, the light is actually going to feel a phase shift, and you then take a interferometric coherent measurement to infer the force signal. Okay, and this sensing technique can be applied to address problems of initial navigation, and also we are currently working with JPL. They are interested in some of the space-based sensing applications using those optomechanical sensors. So this is the experiment that we recently published. So we use a ScreenSlide source to split it into two arms, okay, and these two arms are entangled, okay, and each arm is used to probe a optomechanical sensor residing in a vacuum chamber, and when the light reflects back, okay, you combine it with a reference light to take a balanced homodyne measurement, and that phase coherent measurement will be able to allow you to infer the force signal probed by the sensors. And the other arm, you do the same thing, but the entanglement shared between the two arms would allow you to improve the performance of this sensor system. Okay, so this is the configuration, right? So now you have a laser probe. Okay, so this is the classical case. Okay, without entanglement, you just use a laser, okay, and you split the laser into two arms, and both arms are used to probe a optomechanical sensor, and when it comes back, you take two homodyne measurements, and then you can jointly process the data, okay, at the two sensors. So here it shows the measurement data from each sensor, okay, and when you add up the measurement data from both sensors, you see the signal strength is increased by 6 dB, okay, but the noise is also increased by 3 dB, okay, because the noise at the two sensors are uncorrelated. So overall, you gain a signal to noise ratio enhancement of 3 dB or a factor of 2, and this is actually in line with our prediction, right? So this is a classical sensor network with two sensors, and when you use two sensors, the signal to noise ratio can be improved by a factor of 2. Okay, but now let's look at the quantum case, so the entanglement-based sensing case, right? So now, in lieu of the laser source, you use a squeeze light probe. You split it into two arms and to create entangled probes, and they are used to measure two optomechanical sensors, and this is the measurement outcome, okay, or the measurement data from both sensors. Okay, and when you add them up, the signal is increased by 6 dB, but the noise is not increased by 3 dB. It's less than 3 dB because the entanglement shared by the two arms would allow you to effectively reduce the overall noise when you add the measurement data up. Okay, so then overall, this enhancement is more than 3 dB. It's actually 5 dB in this case. Okay, so it really showed a entanglement enabled enhancement in optomechanical sensing. Okay, so if you can actually plot, you can compare the classical case and the entanglement-based case in the same figure, and as you see, when you introduce entanglement into the system, the noise floor is reduced by 2 dB. Okay, so this is a quantum enhancement, and moreover, the measurement bandwidth is also enlarged. Okay, as you see, this is the sensitivity versus frequency plot. So the black curve is the classical case, and the red curve is the entanglement-based case. And as you see, the entanglement-based curve is wider than the classical case, which shows a bandwidth enhancement. Okay. Oh, okay. Yeah.
So I have two questions. The first is just making sure I understand the intuition. Is the idea basically that since the photon noise, the contributions of the noise from the photons are correlated, that this is essentially where you're winning?
Right. That's right. That's correct. Yes.
So the second question is, on a per photon basis, the different sensitivity?
Yes, I believe so. Yes, because
but you're splitting one photon between two detectors now, in principle, right? So shouldn't this mean that you're getting less, that the competition with a single sensor operated with a single photon source? My question is how much you're winning compared to that case, right? So
Yeah.
Obviously the difference between using an entangled source and a non-entangled source,
Mhm.
you definitely prefer the entangled source, but do you actually win on a per photon basis with a single source and a single detector?
So I think yeah, this is a great question. So maybe I think this can be considered if you use LIGO as an example, right? So our regime is more or less in analogy of LIGO. Because in LIGO, regardless of the squeeze light you use an extremely intense laser light, right? So which would be maybe hundreds of watts. But on top of that, you inject squeezed photons or squeezed field to enhance the measurement performance. Okay, so then if you do a per photon comparison, the energy or the power of the squeezed light is really not on the same order as the initial energy of that laser field. So, but you can use that squeezed field to enhance the measurement sensitivity. So here it's the same scenario. So in the classical case, we just shoot laser light, okay, without entanglement, okay, and the laser light is orders of magnitude more intense than the entangled light that we inject into this system. What we show is that on top of the laser light, you can introduce entangled field, and that would allow you to reduce the noise floor by 2 dB.
So even from the uncorrelated classical sources, you would still see the same reduction in the noise floor?
No, the uncorrelated classical source would just be this black curve, right? So the noise would be uncorrelated across the two senses.
But so if I have a strong uncorrelated field and a weak correlated field, the information I get from the correlated signal drops the noise floor for the uncorrelated photons as well. Is that what you're saying?
So what I'm saying is that, so here is the classical uncorrelated field, right? But on top of this, you can further inject squeezing or entanglement into your system, okay? And that would allow you to reduce the noise floor by 2 dB. It's like LIGO, right? So LIGO, they have a microsync interferometer, and they, without squeeze light, the other input arm would just be vacuum, okay? They split the laser light into 2 arms, okay? But they can also choose to inject a squeeze light into the other arm, which would allow them to reduce the noise in the measurement.
Thank you.
Okay, so that was actually, that experiment was funded primarily by NSF Convergence Accelerator in phase 1. Okay, so in phase 1, we basically put together the prototype to demonstrate the quantum advantage in optomechanical sensing. So now we are in phase 2. In phase 2, we are collaborating with many partners to develop a more compact integrated solution for initial navigation enhanced by quantum light. So what we wanted to do is to develop quantum enhanced gyroscopes and accelerometers enhanced by squeeze light and entanglement to overcome some of the conventional limits. But this is a still ongoing project. Okay. So then, as I said, you can equip each sensor node with a type of sensor. So I have shown optomechanical sensors, but you can also replace the optomechanical sensors with electro-optical transducers. In doing so, you would be able to probe radio frequency or microwave signals, and also use benefit from entanglement in the optical domain. Okay, and the rest of the setup would remain the same. So you just replace the optomechanical sensors with radio frequency sensors. And for example, you can take advantage of a radio frequency sensor network to address problems that are out of reach of just a single sensor. So here is an example. You want to measure the angle of arrival of the radio frequency field. Okay. But to do so, you can use 2 microwave sensors and measure the phase gradient. And that phase gradient would allow you to infer the angle of arrival of the radio frequency field. Okay. And this is a problem that can only be tackled by at least 2 sensors, 2 or more sensors. And here, what we are doing is that you further introduce entanglement into this sensing scenario to improve the performance. Okay, so this is our experimental demonstration. So you have a squeeze light source and you split it into multiple arms. And at each arm, you equip it with a electro-optical transducer to convert the radio frequency signal into optical modulations, and then you use photodetectors to take measurements, followed by post-data processing. Okay, and this is a collaboration with Qingtao Zhuang's group, who did the theory for this work, and this is the main result. Right? So as you see, without entanglement, say you just use completely classical laser light, okay, and the shade, okay, the red shade quantifies the measurement uncertainty, okay, and now you can turn on your entanglement source, okay, and add entanglement into your classical signal, okay, exactly like what LIGO did, okay. So they introduced squeeze light into the otherwise vacuum port of their microsync interferometer, okay. And once we have entanglement on, as you see, the measurement uncertainty is reduced by about 3 dB. So this also shows a enhancement in this sensing scenario, okay. So now I have introduced entanglement enhanced both optomechanical sensing and radio frequency sensing, and we want to further build on our entangled sensor network demonstration to address more complex data processing problems. Okay, so here is an example of a more complex data processing problem. Okay, so say you have a picture, okay, and here it's just a digital picture, and you want to label this object. So this is either a bird or a plane. Okay, so what you do conventionally is that you're gonna pass the digital data along to a classical machine learning algorithm, which is pre-trained by a lot of training data, right? And this algorithm would actually execute on this picture to put a label on this picture, based on its own model, okay? But if you want to further, ask the source of the source of the picture, a lot of pictures or other data formats, they are all acquired by sensors, right? So then we wanted to know to develop a protocol that would allow you to first to program how the sensors are entangled in a physical domain, and with the hope that you can increase the precision of this data classification or data processing problem. Okay, so here, just to give you a comparison between a fully classical data processing problem and a entanglement enhanced data processing problem. So this is a fully classical data processing problem, right? So say you have multiple sensors or multiple pixels to image this object, and they would return classical data, and you pass along the classical data to the classical algorithm, which would label this object. Okay, so then quantum mechanically, you can create entanglement to be shared between multiple sensors. Okay, and you want to, you actually want to first figure out what would be the optimal form of entanglement, which would allow you to address a specific data processing problem at its optimal. So, and this actually pertains to quantum computing, and I don't think necessarily need to show this slide. So this is the very well-known Shell's algorithm, which not only reduces the runtime, but also significantly reduces the power consumption. Okay, but however, building a full-scale quantum computer is a formidable task because quantum decoherence. So we do not have an effective mechanism to mitigate errors accumulated during computation. So now we believe we are in the era of noisy intermediate quantum hardware. And this was a term initially coined by John Preskill also 5 years ago. So in this configuration, you have a reasonable number of qubits, but you do not have a effective error mitigation protocol. And we want to further understand this architecture. Are you able to benefit from NISQ hardware? More recently, there have been a lot of proposals and experimental demonstrations on the so-called hybrid quantum classical machine learning. So the idea is that you have a NISQ hardware, okay, which interacts in real time with a classical computer, and the classical computer is able to read out instantaneously the state of this quantum circuit, and based on the measurement outcome, the classical computer would dynamically configure the setting of the quantum hardware sort of to steer the quantum hardware towards a certain direction of solving a particular problem. Okay, so that is the idea of the hybrid quantum classical machine learning. So this is like, you drive a car, right? So the classical computer is the driver and the quantum hardware is the car, and the driver do need to interact with the car to steer the car towards a certain direction. Okay, but of course, in a longer term, ideally what we want to develop is a autonomous vehicle, which is like a full-scale quantum computer, which would be able to correct its own errors. Okay, but for now, we have to resort to this hybrid quantum classical machine learning structure. Okay, but nonetheless, there are many use cases that are being discovered, including data classification, optimization, and quantum chemistry. Okay. So in our case, in the case of a sensor network, so this is the classical protocol. Right? So classically, each sensor just operate individually or separately, and they would produce classical data, which would be processed by the classical machine learning algorithm. Okay, so this is actually the case of our cell phone camera. Okay, but in the quantum case, okay, so there is a variational quantum circuit which can be configured by the classical algorithm. Okay. And this variational quantum circuit would generate a entangled state or tailored entangled state to a certain data processing problem. And it would produce measurement data, which would be fed to the classical algorithm. And the classical algorithm is going to process the data to label the object. And at the same time, it would update the variational quantum circuit setting. So the hope is that in the next iteration, you're going to generate a different entangled state, but hopefully a better entangled state to address this data processing problem. Okay, and intuitively, you can think about the quantum enhancement this way. So this is the quantum case. Okay, so you have two data sets, this yellow and purple. Okay, and due to the entanglement, you can clearly distinguish between the two classes. And this applies to both the two-dimensional data case and the three-dimensional or higher dimensional data sets. But classically, the noise is pretty strong, so you would have a harder time telling apart the two data classes. Okay, and we did an experiment. So first, we constructed a classical sensor network. Okay, and also we compared the performance against a entanglement-based sensor network. And the entanglement-based sensor network actually shows two advantages. So first, the training time is much shorter. So as you see, it just quickly converges to the asymptotic limit, okay, as compared to the classical case. And moreover, as you see, when they both converge, the quantum error probability would actually be a factor of 2 lower than the classical error probability, which shows a quantum advantage in this data processing problem. And as you vary the parameter of the data set, the quantum error probability also drops faster than the classical error probability. Okay, so actually you see that the gap becomes bigger and bigger, which also shows a quantum advantage. Okay, so this paper was published about 2 years ago, and there was an article written by Seth Lloyd just to summarize our result for this quantum machine learning protocol. So if you're interested, you're also welcome to read this article. So today I talked about the many recent works, including some of the quantum data processing, sensing. I didn't have time to talk about the quantum communication, but there are many other useful applications that I did not talk about, including optimization, physical simulations under the umbrella of quantum computing, but in quantum sensing, you can use it to address chemical or biological sensing problems, or there are also groups building quantum telescopes, and in quantum communication, quantum mechanics would allow you to enhance the security and also enable quantum teleportation for a future quantum network. And then the next endeavor would indeed to build a quantum internet. I believe in the next few talks, we're going to hear very interesting subjects on quantum networks or entanglement distribution. But our ultimate goal is to build a quantum internet would allow us to share entanglement as a fundamentally new resource to enable quantum sensor applications or quantum distributed quantum computing or quantum networking applications. So actually there was an endeavor back in Arizona when I was still there. So we actually built a on-campus quantum network testbed, initially funded by a NSF MRI program. So there are multiple nodes, Sorry. So there are multiple nodes, multiple buildings, and we pull optical fibers to connect all of them. And within each building, there are sub-quantum nodes and a free space link. And at the central hub, we build up many capabilities, including entangled photon sources, single photon detectors, and optical switches, which would allow you to route entangled photons across the campus. And at each user node, as you see, this is a panel. It's actually some fiber resources donated by Corning. There's a panel with multiple, actually 12 links, fiber links at each node, and all 12 links would actually go to the central hub, and then we can use the optical routers to route entangled photons. And but this infrastructure also serves as a very good platform for the training of the next generation quantum workforce. So now I just wanted to show you a demo of how it works. So actually, this is what we call quantum internet service provider. So a user can log in and book their time of using some of the entangled photon sources or single photon detectors. So this is all automated. And this is the state monitor to show the real-time state of the quantum network for entanglement distribution and the remote access to the single photon detectors. Okay. Okay, so this basically concludes my talk, and I would like to thank all my collaborators, students, postdocs, and also funding sources. And again, thank you for the invitation. I'd be happy to answer questions.
I just like to mention that so now I found out about by reading his papers, which we found really interesting. And Kai Tao here is a graduate student that I've been working with at Stony Brook, and he's a pure science graduate student, not a physics graduate student. We were doing some sort of abstract stuff with quantum networks, and you always want, okay, where's the practical stuff? Okay, and when people are really doing things, okay, now you've got your answer. This is the real stuff. Okay. So thank you for an absolutely wonderful talk. That was really interesting.
Thank you, Mark.
Any other questions, Mark?
Yeah, if we have time, I would just, a couple of slides ago, you were talking about data classification and comparing, the classical approach, which I think is pretty easy to imagine what that is, with one using quantum networks. And I was just wondering if you could say a little bit about how a network is involved in the data classification task.
Sure. So the network was involved because we have 3 sensors.
Okay.
And we basically create a entangled state to be shared by all 3 sensors. And then we define a data processing problem, right? So for example, we wanted to measure the field, the mean field, or the average field approached by all 3 sensors. Okay, so we can define this problem, and then we train the variational quantum circuit to generate a entangled state that hopefully would optimally address this problem. Okay, but you can also define a different problem. So we actually also define the problem. So say to probe the angle of arrival of the radio frequency field across the three sensors. So you basically define a problem to be tackled by all three sensors, and then the variational quantum circuit would be trained to generate a optimal entangled state for this particular problem.
So it's really in the generation of the data that you're actually classifying.
Yeah, it's the generated data that you are trying to classify, right?
Please explain a little bit about the measurement process and the post processing stuff.
Yeah, so here our measurement is a homodyne measurement, so which is basically a phase coherent measurement. We measure the quadrature of the light field, okay, and the post processing. So here, for example, in this entangled sensor network case, we just use a classical, very well established support vector machine to do the data classification.
And is there something between them? So you feed some data into the support vector machine, and is there like some pre-processing?
Yeah, it does some pre-processing, but it also does an additional step in the quantum case. So it would reconfigure this variational quantum circuit, okay, to generate hopefully a better entangled state for the next round of data classification. So it's a more like a interactive process between the classical processor and the quantum circuit.
Yes, I read this data before, and I don't know the details, like how do you like back propagate the loss? Like, you need to adjust the variational quantum circuit. So I think there's some technique that there's a loss function for the machine learning.
That's right.
Then you need to back propagate the loss in order to adjust the circuit.
Mm-hmm.
And I'm not, maybe there's no offline, we can
Yeah, sure.
discuss more about how do you back propagate the loss.
Of course, yeah.
How much control do you have over the quantum state that you're producing, or is it sort of regulating the amount of squeezing or something, or is it?
Yeah, right. So that's a great question. So here, so what we can control is the splitting ratio of the beam splitters, and we can also apply an additional phase onto the states at each node. Maybe there's a question online, I think.
Yeah, I was wondering about that. Look at the chat and see if there's someone has.
In the example, so the question is, in the example you show regarding quantum sensing gains, higher SNR than a classical version, are the number of the photons used in the classical and the quantum light same? Yeah, almost the same, because as I explained, so first you have to use a very, very strong classical light like LIGO, right? So with in our case 100 microwatts of power, but the quantum light we add in only has a few nanowatts of power. So I would say almost the same.
Okay, are there any more questions? Okay, I guess if not, then thanks speaker again, and we'll move on to the
Thank you very much.
that was very interesting.
Thank you, Mark.
The next speaker is Max Wolf from the Sandbox.
One familiar with this platform?
Yeah, I guess.
Oh, I guess we log into.
Have you logged into Zoom?
No, I have not.
Okay, so in our Slack, you're on the internet,
Yeah.
right? In our Slack, if you go to the Sandbox channel, I posted the Zoom. Here we go. And then just make sure your camera's off, your microphone is off, and share your slides.
wrong. Sorry for that. Just give me a second. I think I might need a brief help from you, Mariana, about that. I think now we're good there.
You should be good. Just make sure it's mute. And your arm.
Mute I was, yeah.
You mute and then make sure your audio is turned off on your computer, otherwise you'll get feedback.
Yeah.
Okay, and then. That's you.
All right. Sorry for the small hiccups here. Hi, everyone. My name is Max Ruf. I'm a research scientist at Sandbox AQ. I decided to shake up my talk a little bit in coordination with Mariana. And actually, I want to split it in two. I first want to talk about like Sandbox AQ and the different product areas that we have at Sandbox, because I feel like talking to some of you, it's maybe not so clear to you. What is Sandbox? What do we actually do? And I think that could be a goal for all of you to go home and have an understanding of what Sandbox does. And then the second half, I'll actually talk about work that we did in my PhD labs. So I did my PhD with Ronald Hanson at QTech in the Netherlands. So I'll talk about entanglement distribution network experiments there. Just a little bit about myself. I thought I'd share some pictures so you have a little bit of an idea about the person here and not just maybe the science behind it. So I was actually born in the Bay Area, but grew up in Germany, as you can probably tell by now. I then did high school over there, had some fun flying glider planes, and I love to talk about this like in the coffee breaks or something. And I then went to Canada to do my master's degree. And of course, in Canada, you got to play in the intramural physics, one of the intramural physics teams that is, you know, we played some hockey, let's put it that way, and got to wear some good outfits. And then I went to the Netherlands to do my PhD. So I picked up some kite surfing, had some fun, well, sometimes fun in the clean room, a lot of time spent in the clean room. Here's a facility that we use to electron irradiate our diamonds to actually make nitrogen vacancy centers in diamond. We were also sometimes posing for photographers. And then at the end of it, well, you defend your PhD and you get to wear like a funny suit and get a red pipe that contains your PhD degree. Yeah, so let me first give you a brief overview of Sandbox AQ. So I think Mariana mentioned that already earlier. The pedigree of Sandbox is to bring together the worlds of artificial intelligence and quantum. And it's our CEO's Jack's belief that the nexus of technology is where big innovation actually happens. So if you bring together two fields, then there might be great innovation happening. I think the timeline Mariana already shared. Here's a picture of Jack, our CEO, who funded the group in 2016. The name Sandbox comes from like the playground of one of the founders of Google. So it was his sandbox. And then AQ is for AI and quantum, in case you've ever wondered about our name. In 2020, Eric Schmidt joined, who's now the chairman of the board. We spun out of Alphabet in 2022. We are a completely independent company at this point in time. And right now we have about, well, the employee number is very fast growing, so I won't give you a precise one, but it's well over 100. And we're spending across North America and Europe. Right now, it's about 60% of people are in North America and 40% are in Europe. And we expect this to change actually in the next year or two and kind of go the other way around. So probably more in Europe than in the US. Mariana mentioned this very briefly. We have three main product areas at this point in time. We have the simulation and optimization group. And actually, Nadia and Adam just joined us that are sitting in this group. We have the quantum security and communications group. And then we have the quantum sensing group. And I actually sit in the quantum sensing group, mainly focused right now on bringing together our sensing platforms with potential problems that clients might face, and if we might be able to address them and how we might be able to address them to them. So the first one I want to briefly talk about is this quantum security and communications suite. So I guess it was even mentioned in the previous talk that quantum computing might pose a threat to the way that we encrypt our data right now. And that's because of something called Shor's algorithm that I'm sure very many of you are very familiar with. It threatens to break that encryption. So I would see this as this is one reason for people to be like, okay, we need to tackle our cryptography system. And that's, not a topic maybe that's very sexy inside an organization. It's not like how you maybe get the next promotion or something. So it might not be, on everyone's mind all the time. But actually the problem is much bigger that organizations have. And that is that right now they don't even know what kind of encryption they are using. And you can think about it in the following way. So let's say you're like one of the big banks of this world. You do 10 or 15 acquisitions per year, and you've patched together this network over the many years, and you don't know what kind of encryption mechanisms you're using where in your network. So one of the things that we found is where we can help customers quite significantly in preparing this transition here right now to actually analyze these networks and give them an overview down to the source code level of where is a certain cryptography algorithm called, and then also have user profiles and basically check, well, is this in accordance with the policy that I want to be using, or where are my vulnerabilities in the system? So this is a product that we have on the market right now. But we actually want to go into something bigger. So this is the discovery suite that I was just talking about on discovering where cryptography is used in enterprise at the moment. But we want to go into an automated remediation mode further down the line, and planning to release that sometime at the end of this year or so. And the idea here is to then, well, once I've detected these vulnerabilities, I want to be able to actually remediate them. And that's something that can be very hard, because the way that a lot of applications, I've been told, are coded at this point in time is that the cryptography is fundamentally coded into the application code. So they are not like separate software layers. And so it's actually quite hard to separate this out. And this is why people have not really tackled this problem, even though it has been kind of looming over them for a long time, but maybe they are like the threat wasn't high enough for them to tackle it. Now with quantum computing, it's like come to the surface again. Now, of course, the question that you might be asking yourself, well, what do we actually want to use to remediate it? So right now, our main focus is actually in post-quantum cryptography. Probably a lot of you have heard about NIST process on standardizing algorithms here. Sandbox has submitted and is actually on most of those schemes. So this is the main focus right now. So this is a software-based method, basically a new paradigm of mathematical problems that we believe right now are hard to crack even for a quantum computer. But of course, there's also other tools, like you can think about QKD or many other tools out there. And we really see ourselves as what we are building here is the overarching cryptography control plane and analysis. And then we will slot different tools into this toolbox. Right now it's PQC and some QKD maybe, but we might also be flexible on this in the future. The second one is simulation optimization. Since Nadia and Adam are here, I'll just ask one of them to actually come up and talk for 2 minutes about what you're doing, because I'm sure you can do this much better than me, and I don't want to offend you. So this is a very Sandbox move to just call up someone and let them speak about some slides.
Do you want to come too? There, just so you get visibility. So I'm Adam Lewis. I'm the technical lead for the simulation optimization team. This is my boss. Yeah, this is my boss, Nadia. So we're one of three. So our group is concerned with performing both quantum and AI-based simulations and optimization. By quantum in this case, we mean, well, it's a sensitive word in the industry, but I think in physics world, we call quantum-inspired algorithms at this point, which are algorithms that simulate entanglement classically, such as tensor network algorithms, and track the progress of quantum computing and allow for like a subset of what you might have thought, unless you took an entanglement-based approach for devising the algorithm in the first place, would have been a purely quantum problem. But in fact, in some special cases revealed by that formulation, actually can be sped up on classical hardware, of course, relative to a previous implementation. But more widely, we're actually taking a more problem-focused approach. I don't know what the next slide will be, so we're going to go on a little bit of a journey together. Okay, yeah. So So we're taking a more problem-focused approach onto impacting upon actually drug discovery right now, which we've targeted as an area where there's a peculiar need for improvements in the simulation and optimization of quantum relevant systems, such as electronic structures. On this slide, just, I mean, the exact numbers don't matter, but the point is that drug discovery is a big, expensive market, basically. It takes a long time to develop a drug. The exact number is a little confusing because how this actually works is you get a drug, you bring it to market, and it probably fails. And the way it usually fails is in clinical trials. And the reason it usually fails is that it wasn't effective. So the numbers you're seeing here, 1 to 4 billion, are actually like amortizing over that failure rate. So the per program failure rate is lower than that, but this is the overall cost to get a drug to market in the eventual book of an industry. So what we work on is making, this is actually slightly misleading. We work on making drug discovery cheaper and faster. Drug development is a slightly different thing. And we do this by developing new in silico algorithms to develop new molecules, to model their properties and optimize over them to give a new property. Oh, and that's the end of the journey. There's more slides, but I just wanted to give you a quick overview. Any questions?
Yeah, please.
So, you know, I hear about this in drug discovery. Is there something in the biology problem that suggests that tools that come from tensor networks that have sort of low rank tensor factorization to some quantum state are relevant for drug discovery?
Yeah, for sure. So there's, I mean, so I can give 3 examples. The first and most obvious, which is the one we're indexing on. Now, be clear, we're not only doing tensor networks quantum inspired. We have like a broad range of algorithms and simulations. But the question is, how do tensor networks bear upon drug discovery? So an important question in drug discovery, and kind of the one that is kind of what comes to mind when you think of physics-based simulations of drug discovery, is called binding affinity prediction. Is this a whiteboard or like a wall?
It's a whiteboard.
Okay. So like this squiggly guy is going to be a protein.
You know what? Can you write it behind the podium? Just
Over here.
I just feel like it's
Right here.
But yeah, I just wasn't sure if this was a whiteboard. I don't want to like graffiti up your wall. So this squiggly guy is also a protein, and then like there'll be a drug and a molecule, and then there's a binding site identified, and you want to know like the free energy difference between this thing being over here and this thing being there. That's called the binding affinity. And to estimate this, for reasons that, you know, I don't want to go into exact details, but it's necessary to know the electronic structure surrounding this and also in the vicinity of the binding site. And in many interesting cases, that binding center contains what's called an organometallic complex, where it's like has a very heavy atom. And this, for when you actually work out the quantum chemistry, basically you find that this system is in tensor network language is like reasonably like more in, well, it's not highly entangled, it's multi-reference, which means that traditional approaches to quantum chemistry don't handle it well. This is a very specialized example, but it's very relevant to like say toxicity predictions, because some of the enzymes in the body that break drugs down are in this class. You'll often hear people talk about like Haber-Bosch, not Haber-Bosch, it was like, I forget the name now, but this is like fertilizer. Like whenever you think like this, whenever you like, people like, oh, quantum computers are going to be useful, they talk about this nitrogen fixation problem.
Yeah.
And that's an example of this organometallic complex, although in a different context. So using a tensor network algorithm, you can do the electronic structure simulation on like GPU networks at like a very favorable cost, which would essentially be impossible using, say, DFT and so on. And that's,
it's like matrix product states or?
Yeah, I mean, it could be a matrix. Like we're using matrix product states, but it would the exact form of the tensor network, you know, it isn't. It's just would depend on the specific system, I think. But an MPS could work, right? Yeah. Is there a question? Does that answer your question before I run?
Yeah.
So that's only one example. The other ways are using
the biology, but I think.
Yeah, so the first is just measuring the free energy difference between a molecule being unbound versus bound to a protein. The second is these quantum inspired algorithms, which don't necessarily treat a quantum system, but they do what you would have thought was a quantum computation. So there's examples of this for like doing a quantum Fourier transform using tensor networks. Of course, you can't do it for arbitrary input because then you have a quantum computer. But you can do it, it turns out, for a special class of inputs at like a speed up relative to MMT. And so using these things, we can also impact upon Fourier transforms and in particular discrete optimization. So there are classes of discrete optimization problem where you can get a speed up relative to standard approaches using tensor networks, basically.
Yeah.
Yeah, there's a, go ahead.
Is it also applicable to protein folding?
Well, protein folding is probably, I mean, these days it's really treated with deep learning. What we are kind of interested in with this is sampling. So what like say AlphaFold tells you is like the lowest energy state of a protein, but actually to get the accurate binding affinity, or in many cases, some proteins don't have a binding state. They actually fluctuate kind of meaningfully. So what you really want is like a sampling around the lowest point that gives you like a reasonable picture of like the thermodynamic ensemble. And you can use both tensor networks and these AI approaches to get that confirmation working on coupling. So that's protein folding itself is, I wouldn't quite say it's solved, but like it's not nearly so challenging as it used to be to predict the lowest energy state, but getting the fluctuations remains a very difficult problem and something we're very interested in. Did you have a question? Okay, then I'll give the podium back.
Thank you.
Yeah.
Decision because you answered these questions much better than I would have ever been able to. Thank you for that intermezzo and being so spontaneous. So now I'll talk about something that I'm actually qualified to talk about, which is quantum sensing, because that's the division that I sit in. So our approach to quantum sensing and maybe how we differentiate from a lot of other players on the market at this point in time is to say, well, we're actually working on 4 or 5 different hardware platforms at this point in time. And we're trying to match those with applications for customers. So this actually tells you quite a lot of how we view the world in a sense at Sandbox. So we take these sensors and we typically actually do some studies for customers to actually figure out also what sensor, or actually typically what turns out what system of sensors is best to use here. It's often in the data aggregation actually what we're doing. And then we need to denoise and control that, and want to have like some users that we can sell some software to. Right now, we're basically using these quantum systems often in what people would probably call more like the classical sensing regime at this point in time. So the first application that we're working on is quantum navigation. And so the idea here is, well, one of the threats that we have is that the GPS jamming is a daily occurrence. And on this slide here, you can see for one particular day, a map of the world and where GPS jamming occurred. So of course, we're all very reliant on GPS telling us where the hell we are. Even this morning, finding this building, I couldn't have done without GPS in my phone. But GPS has critical weaknesses. So like the first one is, okay, it has some human cost, access and attacks. Like it can be relatively easy jam. You can buy a device on eBay for $1,000 or $2,000 that will jam it in some radius around you. And there's some other attack vectors here. But also it has some technical limitations, for example, signal deflections or certain areas of the world. And in particular, also no underwater or underground signals are possible. And so what we are interested in is in having an resilient alternative navigation technology. So it's not necessarily meant to replace GPS, but having a resilient alternative backup system also in a lot of use cases. The idea here is to use the magnetic fingerprint of the Earth. So basically every point on Earth, of course, has a magnetic field associated with it. And because of Earth's formation, that actually really is a fingerprint that varies depending on where you are on the position on Earth. And then what you want to do is you will actually typically use some inertial systems that will tell you, right, in principle, we all know that from physics principle, if we were to measure a speed and acceleration, well, then we should be able to always back calculate where have we gone in a certain time. But the problem is that these systems actually drift over time. And so your position accuracy actually drifts away exponentially with time. And so what we basically want to do is to use magnetic maps and sensing of magnetic field to anchor that drift of the INS. So we've done some studies that were published with the US Air Force. We're right now also working with the US Air Force and also other players in that field. The second application that's a main focus area for us right now is magnetocardiography. So I think we're all familiar with going to the doctor and they place some electrodes on you and then you see some heartbeat. And we're basically trying to do the same thing, but measuring the magnetic field of your heart rather than the electric field. And that at a high level has some advantages because tissue is pretty much transparent for magnetic fields versus it has signal deflections for electric fields. And so that means that there's some complementary information that would be available in the magnetic field. Of course, I think the motivation here, okay, cardiovascular disease are a massive problem, number one cause of death. There's a large fraction of those that can't be rapidly detected at this moment in time. So this is something that has actually been studied in literature quite well, and people have established that this is a technique that allows you to rule out certain heart conditions that you can't right now. So you would go to the hospital, they would draw a blood sample, look at some indicators in your blood, and give you a result 1 or 2 days later. But in those 2 days, you're in the hospital, and either you should have been operated already, or you're like costing massive costs to the health care system, but you could have gone home after 5 minutes. That's what we're trying to solve. And the key differentiator for us here is to do this at room temperature and unshielded. So a lot of you might have seen squid-based systems before that typically operate in shielded rooms and require cryogenic cooling, so they're very expensive. And for us, we're trying to do this at room temperature, unshielded, and at low cost. And then we want to combine this also with AI tools for clinical decision support, so not replacing the doctor. Those are our 2 main applications in quantum sensing at this moment in time, where we're all working with partners. Here we're actually just put a blog post up stating that we're like testing this device in a hospital right now. But we are also actively looking at other areas in sensing that we could match our sensing platforms. And as I said, we have like 3 or 4 different hardware platforms at this moment in time in our labs, which are based in Palo Alto. All right. I wanted to say 2 more things about Sandbox. I think the first one, Mariana already said, right? The education team is doing great work, really building up this ecosystem. And it's great that we can have a workshop like this here, also partly supported by Sandbox and the internal learning culture. The second one is that we have a strategic investment program that Mariana also touched upon. We typically only issue smaller ticket sizes. But the idea here really is to say, well, can we grow the ecosystem here and maybe bring in investors that traditionally wouldn't invest in quantum technology because they don't have the technical expertise necessarily to evaluate, is this a promising application? Does this make sense from a product perspective? Is there a market? But Sandbox might be able to deliver that. And so that's really a way that we also see of growing that ecosystem for the future. I'm now going to shift complete gear and talk about my PhD work on quantum networks, actually. And since this is an education workshop, I actually designed this talk relatively, introductory level. If you get bored at any point in time, then please let me know and we can also skip some slides or talk about other things. I want to start by setting the scene a little bit. Who of you knows what this picture is showing?
Is that one of Von Neumann's computing machines? Is that like the Maniac?
No. Okay, let me talk about a special moment in time, which is 1915, the Pacific Panama exhibition. It's this exhibition in San Francisco where San Francisco had been struck by a massive earthquake in 1906, which had devastated like half the city. And it's this moment in time where they make a fair and kind of show technology to the world. And it's kind of saying, hey, San Francisco is back on the map. And one of the exhibits that American Telegraph and Telephone had actually promised for that workshop was a coast-to-coast telephone call. But the problem was, it was actually technically impossible at that moment in time. And that was because the signals over this long distance got so attenuated that it basically became inaudible. So what this is showing here is a very early version of Audion Tryon repeaters that were used for classical telephone networks. And I want to argue that the goal of my talk today is to convince you that I believe we're roughly the same moment in time, but for quantum networks. I really like this. I really like quotes. In particular, this one by Claude Shannon in 1959, who said, I think this present century will see a great upsurge and development of this whole information business. So of course, he's the one with the concept of information entropy, amongst many other things. And this person here, maybe someone knows who it is. This is very hard. I wouldn't know. So this is Bill Duval. He's the guy who received the first message over a classical computer network, like at Stanford back in 1969. So he is the guy who received the LNO before the system crashed, as we probably all have heard famously. And I just want to say here that this was in 1969. Now, 50 years later, we're sending 9.1 billion gigabytes of data over the internet every day. So that, I think, shows you that rapid evolution of technology, and of course also how our life is not really thinkable anymore without the internet these days, right? Anywhere you go, the internet is the first concept. And what is the internet? Well, it's like a combination of computers that are strung together, and here the classical repeater to boost signal strength is an important component. Now I'll give you one more quote, and then we're done with quotes for today, which is by Erwin Schrödinger from 1952, who said, "We never experiment with just one electron or atom. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences." Now, 70 years later, of course, we're building these things actually in the lab, and we're trying to make them practically useful. So here you can see, well, okay, it's maybe not the best metric, but the number of qubits growing over time, or like here, proving Einstein wrong about spooky action at a distance in this famous Bell test experiments. So you can see also here that rapid evolution of technology. Now, what is a quantum network, or what is a quantum internet? I'm depicting it here, somewhat selfishly with the NV centers and diamond nodes, but that's just a small side note. It's not important to the concept. It's a network of quantum processing units that are strung together. Again, a key component, and I would argue the missing component right now are repeaters in the networks. And of course, the goal here is to enable entanglement generation between any end nodes on the network, and have that entanglement available for resource for applications. This, I think, is a little bit hand-wavy maybe, but really there's two special. I like to think about it in terms of, okay, why entanglement? Why is it useful? Two special features of it: maximum coordination, so stronger than classical correlations, as probably most of you know. And the second one, inherent privacy. So like something where if two qubits are maximally entangled, it's impossible for a third person to be just as entangled with them. And I think a lot of applications at a very high and rough level, and please don't now go into the details and bash me for what I'm saying, but like you can somewhat understand or like think about in that concept with these two things in mind. This is probably a graph that a lot of you have seen in this context. This is a paper written by Ronald, my PhD advisor, but then also Stephanie Wehner and David Elkus, which talks about the use cases of quantum networks, in particular the functionality stages. So here, every stage that's going to appear is basically enabling new capabilities. And I think over the course of this workshop, we're going to hear several talks that touch upon a lot of these different ones. Here's the time axis, and then an increase in functionality, but complexity. And then I've somewhat, these are my own assessments, grouped it in, okay, where's the field roughly at for these functionality stages? So it goes all the way from point-to-point quantum key distribution over those, prepare and measure quantum key distribution networks, to device-independent quantum key distribution, to blind quantum computation, to small distributed quantum computation, and then to large-scale distributed quantum computing. And I believe that at every of these stages, there's some value actually to be had for organizations, and that's probably one of the reasons why Bart is here with his affiliation at Amazon this week, why they believe in this technology. But I'll let him speak to that.
The text, the diagonal does increase in functionality, but complexity.
Yeah. Sorry, maybe not in like a mathematical complexity sense of the word, but like in
I'm not sure how the two are, why are the two connected by a but and not an and or?
Well, because I think that's a mindset. That's like the glass half full or half empty question, I guess, might be what we're getting into.
So functionality comes at a cost of complexity.
Exactly, right? I mean, in principle, right? Like if it was like the other way around, well, okay, and why would I not go for the holy grail right away, right? And do everything that I can do underlying. But it's, you know, it's much more resource intense, will, you know, take like 10, 15 years of development time. So that's how you should understand this. Okay, so, how do we build such quantum network? I think it's an early stage really in the field right now. And there's many node platforms that are interesting and that people are, you know, experimentally working on. I've listed here a couple of them. This list is not exhaustive, and there's other ones that people are also interested in. I just wanted to give you some flavor here, and I've also mentioned here maybe the key papers for mostly focused around entanglement generation in these systems to date. I would say there's not really a clear winner at this point in time, and actually I would go one step further and say what's probably gonna happen in the future is that you want a combination of different technologies for different purposes. I think what's very exciting for the technologist part of me is that we're seeing a lot of commercial activity starting to enter the field. And I think it's really this engineering that we need. So there's a couple of companies again listed here. Of course, this list is not exhaustive. Okay, now I'm gonna talk about, for the rest of this talk, I just talk about this because that's the topic I did my PhD on. And in particular, I'm talk about one specific defect in diamond, which is the nitrogen vacancy center. And I'm sure that Bart will talk about other defects in diamond tomorrow. And I want to take you on a little lab tour actually of today and look through the lens. And we're going to go to Ronald's lab and actually try and find the diamond V center. So, okay, let's go. This is when you would enter our labs, and you notice like some kind of scale bar here. You have large optical tables. This is actually an earlier version of our setups. By now, more of it is fiber coupled. You would have a lot of professionally hung cables from the ceiling. And then some cryostats that a lot of laser beams would go into. So our experiments typically work at 4 Kelvin, and that's to freeze out phonon processes in the diamond. Typically works below 10 Kelvin. If you then zoom in further, you can start to see the cold chamber of a cryostat, a 4 Kelvin closed cycle cryostat emerging. You go even further, and you see a sample holder that is used to thermalize the sample well, and here a PCB that's put on top of it. You go even further, you see some diamond chip emerging, and they're actually typically 2 by 2 or 3 by 3 millimeters. And then a lot of wire bonds. For those of us that were there yesterday at Javad's lab tour, we were looking at some of those pictures in his lab, and well, let me say, putting those wires on is a pain in the butt, but that's a different story. Then you go on further, and you can actually see that these wires are ending on top of the diamond on some gold electrodes that are going by some small, what look like in this kind of microscope setting, black dots. If you zoom in further, you actually realize that what's happened here is that we've milled some diamond material away on the top surface. And under each of those, what we call solid immersion lenses, there would be an NV center sitting, typically a couple of them, but we would talk to one of them specifically. And the goal here is that you would have some microwave strip lines, so to drive the spin transitions of the system, and I'll talk about this in a second, but that you'll also be able to apply electric voltages to actually tune the transition frequencies of different NV centers into resonance with each other. Yeah, and this is like close up of the solid immersion lens. The point being here, the diamond is a very high refractive index material of about 2.4. And so you get a lot of total internal reflection if you don't mill such lenses around the diamond. So you want as much light out of the system as you can get. I want to highlight here that a lot of what I'm going to talk about on the experimental side of work, that's like really, generations of PhD students in our lab. And also, so this is my PhD supervisor, Ronald, this is Tim, another key PI in Delft working on NV centers. And so I just want to be very upfront about this. This is not all my work that I'm going to talk about today, just to be clear. So what is an NV sensor in diamond? An NV sensor in diamond is it's a nitrogen vacancy sensor. So typically, as you all know, diamond is made out of carbon atoms. But here there's a nitrogen atom that's substituting one of the carbon atoms next to a white vacancy. This system in principle has 6 electrons. We can forget about 4 of them because they're paired. Then you basically have a spin triplet system that you're left with. And here I'm plotting the energy transitions of that spin triplet, where with a magnetic field, of course, you have the Zeeman effect, they split up. And typically the way that we form a qubit state here is by only addressing like 2 out of those 3 lines in our experiments. I talked about this a little bit before, where we have the solid immersion lens with the NV sensors in them. This here is a gold strip line to drive microwaves through, and actually drive these spin transitions, rotations. And these are here the electron, the gates to apply electric fields. And here you can see some Rabi oscillations of the spin measured at room temperature. Now, what's going to be important to understand is, I don't want to really go into the whole level structure of diamond. That's somewhat complicated. But you have a ground and an excited state. And depending on which spin state it's at, the system is in, you actually get what we call spin pumping transition and readout transition. So they have a different cyclicity, these transitions. So if you start pumping on a certain line, if you're on what we call the readout transition, it will go under a lot of optical cycles. So go to the excited state, or get to the ground state, or up optical, before the system goes dark, and it would get pumped into the plus minus spin state. Versus if you did the reverse and were pumping on the plus minus 1 state, it actually is very effectively pumping you into the m is equal 0 state. What that means is you have a way of initializing your system fast optically, but also of reading it out. And the system works at 637 nanometers, so in the red light. Now, what's also important, and I didn't really want to put graphs on this, is this graph here, which is you're pumping the system quite hard on here with the green light, and actually the diamond lights up red. So like these are the transitions that we're looking at. What's happening here? How is this possible? You might ask yourself, where does this energy go of the green light? Well, there's some phonon sideband actually. So this goes into lattice vibrations. And this is one of the bigger problems of the NV centers. So you only have 3% of the light in such transition is emitted without a phonon. And it's only that light that we can use for entanglement generation. So like 97% of the light we can't use. And that's one of the reasons why people are actually looking in other color centers in diamond, because the spin properties are outstanding. This I just talked about. What this allows you to do is what we call single shot readout. So you can, after a very brief amount of time, you park your laser on this readout transition. And then if you get a photon, it's very likely that you are in this MS equals 0 state. And you can do this for a little bit of time before it would get pumped out of that state. And so that allows you to say, well, if I catch a photon, then I'm in the MS equals 0 spin state. If I didn't catch a photon, then I was in the MS equals plus minus 1 spin state. Yeah, and at room temperature, I wanted to say that at room temperature, the reason why we cool our systems to 4 Kelvin is actually that not the spin. So the spin properties are actually there at room temperature pretty much as well, but it's the optical toolbox that's not available. In particular here, you don't have these spin resolved optical transition that are needed to initialize the system and read it out effectively, and also to generate entanglement, as I'll explain to you later. So that's why we go to these low temperatures. Okay, now we haven't talked about something important around the NV centers. Actually, that's the environment of these NV centers. So far we've had a graph, and I hope I explained you this part here well. And then in principle, most of the carbon atoms around the NV centers are carbon-12, and that doesn't carry a nuclear spin. However, in natural occurring diamonds, about 1.1% of the carbons are actually carbon-13, so a different isotope. And that one has a nuclear spin, so it's a spin half system. And you can think about this. What would this do? Well, you would first think, it's probably not going to be very good if I have some fluctuating spin bath in a semi-classical picture, like some spin bath around my NV centers. That should lead to a lot of decoherence, and it's probably not a very good system. And I might want to, you know, purify the hell out of my diamond as I grow it. So these are typically lab-grown diamonds to get this concentration as low as possible. Turns actually out that you can use those instead of a bug as a resource, as I'll hope to be able to explain you in a second. And what you're looking at here now, in going into this explanation, is a dynamical decoupling sequence. And actually, I'm realizing I forgot, so this should be brackets around it and to the power of n around the pi-pal section. But anyways, for the experts. And what we're looking at here is the electron spin coherence as a function of the decoupling pulses on the right axis, there's n. And you can see nicely that this fits some functional form, which is a cubed term that you get for a fluctuating spin bar. And it shifts to the right as we do more and more decoupling pulses. But if you look closely, you can also see that there's some kind of deviations from the trend here in the data. And so the question you should be asking yourself is like, well, what's happening actually at these weird points in time when this is dying? If you zoom in further, you can actually do an experiment where you do this a little bit more controlled. And you can see that some spikes become visible. So you would put the NV center in an X state, and then do some dynamical decoupling sequence, vary the decoupling time here in the sequence. And then you can see some pattern emerging where there's some spikes that go all the way to -1 or maybe to 0. So what has happened here? Well, at 0, as we know, that means the coherence of the NV center is gone. And at -1 is basically interacted in a coherent process with something in the environment. So the big question is, of course, well, what the hell happened? This is here data for 3 NV centers, actually. And what you know, if you look at it a little bit longer, maybe, you can see that these position of the dips, they don't actually all like appear at the same times here. And they also don't have the same depth. And so that tells you immediately that this feature that we're looking at here is something that's not around, like nothing intrinsic to the NV centers, but it's actually something that must be happening in the environment of these defects in our diamond. And it turns out that what you're looking at is what these spikes are interactions with the different nuclear spins that you have in the environment. And we can actually now use this to our advantage. So of course, these are like coupled via the hyperfine interaction. And if there's a different Hamiltonian, depending on the electron spin state. And in particular, what's important about this one here is that in the MS=0 state, you have a certain rotation axis. But in the MS=1 electron spin state, that rotation axis for the nuclear spin actually tilts. And what this means is, well, if I have a way of having, you know, one rotation axis and another, that means I can do a universal gate set, because now I have all control in principle to rotate this thing in any direction. And so this is what we typically use in our experiments to actually turn these nuclear spins from a bug into a feature and use them actually as very coherent memory qubits in our system. So we would have one electron spin qubit that you can use for optical initialization and readout, so kind of to access your local quantum memory. And then you have many nuclear spins in the surrounding that you can use, for example, for memory or some other operations. I don't have so much time left, so I have to go quite quick here. I just want to now tell you about 2 or 3 like research highlights from the NV system platform in particular. So these are results mostly from my colleague Mohammed in Delft, where they've really gone through some quite rapid, how do you say? I can't say this word, sequence of events in experiments. So what they first did actually is that they characterized the environment of one electron spin in very great detail, and they were able to reconstruct the exact lattice positions of 27 spins in the surroundings of an NV center. And then they used this and used the 5 best qubits of this to do some error correction code operation on NV centers in diamond. So of course, the idea of that is that instead of like encoding quantum information in each physical qubit individually, you would spread that quantum information out onto many on one logical qubit that's comprised of separate individual physical qubits, and then be able to do what we call stabilizer measurements to actually detect error syndromes, and that way be able to correct errors on the qubit. What they did here in particular is a 5-qubit core with a flag qubit, and that flag qubit is here to actually correct for errors on the readout qubit that we have in our system. So the NV electron spin. And I think one of the highlights, I really don't have much time now to go into this, is that they would be able to have real-time access to these measurement during the stabilizer measurement outcomes and be able to operate this on that, which is something, of course, that you would need if you want to build a fault-tolerant quantum computer. I should say that the logical error rates was not below the physical qubit error rates in this experiment. Still, of course, that's the big breakthrough that you're hoping to achieve. Okay, now we've kind of established the NV center. We've established a carbon platform around it and how we can turn this from a bug into a feature. Let's talk about how we actually create entanglement between NV centers. So like between 2 distant processing nodes in my picture that I had earlier. So for that, what you typically start out with, you initialize the system optically in the m is equals 0 state, and then you put that electron spin in a superposition of the 0 and 1 spin state. And yet then you apply a photon. So you have these 2 NV centers, they're both in the superposition states. You apply a laser pulse to each of them. That's such that if the electron spin was in the m is equals 0 spin state, it would emit a photon, and otherwise it won't. What it means, if I then take these spin photon entangled states and send them to a beam splitter in the middle, and these photons are indistinguishable in all degrees of freedom. If I look after that semi-transparent mirror and I detect exactly 1 photon, well, what does it mean? I know that one of those NV centers was in the 1 spin state, and the other one was in the 0 spin state, but I don't actually know which way around. And so that means that you then can end up with an entangled state of this form here. Now, I don't know how much technical detail I should give you here. Of course, there's actually a lot that you have to think about when you want to do this in practice in the lab. There's a lot of limitations. And in particular, you could have a probability that actually both of them were in the 1 spin state and emitted a photon. And then like, how do you get rid of that? So traditionally what people did is they would actually always apply 2 of those optical pulse sequences after each other and invert the spin population in the meantime on each individual node. And that way, basically, only if you have the photon twice in a row, that would mean that both of the NV, that really was one NV center emitting a photon and the other one not. People then realized that this is actually not the greatest way because that really limits your success rates. It basically goes like cubed in like to 10 to the minus 4 cubed is a small number. And so what people then did instead is come up with a single photon entanglement protocol. And here the crux to that is that you basically put those NV centers in a superposition of somewhat a little bit more biased toward the bright state and the dark state. You would only detect 1 photon here. And then you just need to trade off probabilities of that bright state population, which influences your state fidelity, but also your rate. And I don't have the time, unfortunately, now to talk you through this. But I just want to say that, like, I think conceptually it's quite easy how to make entanglement in these systems. But then how to do it in detail, there's actually a lot that has to go on in the hardware and also in the real-time control of your system to charge resonance check, make sure everything is on resonance and so on. And that's really the crux of these experiments, I would say, is like a lot of software engineering actually that goes into running these setups. Now I'm almost at the end of my talk. I want to leave you with this quantum teleportation experiment that my colleagues did in Delft, where you would have 3 nodes. So Alice, Bob, and Charlie Bob and Charlie in the same lab, and then Alice in some lab, like a couple of tens of meters down the line with some noisy rooms in between, which are pain. And then Charlie and Bob would have you would use here one NV center with one carbon spin next to it. And the way the goal here is to teleport an arbitrary quantum state from Charlie to Alice with unity efficiency. And the way that this works is that you first need to prepare that heralder. And so, of course, we only have in our system, as I said, one optical interface per qubit system. So we would generate entanglement between Alice and Bob using the single photon entanglement protocol. You would swap that state on Bob into the memory qubit that frees it up to actually generate entanglement between Charlie and Bob. You would then do a Bell state measurement and feed-forward operation, so entanglement swapping, to actually generate entanglement between Alice and Charlie. And then that point in time, you would have a basically the teleporter heralds to you as a user, hey, I'm ready to teleport entangled state, as in like I have this entanglement established here. Give me a state to teleport. So you would swap that over, prepare a cardinal state on the electron spin state here, do a joint measurement and a feed-forward operation, and then that state would show up at Alice with a fidelity of, I believe it was about 0.7 or so, and at a rate of one event every 2 minutes. So of course, that's cool in principle, and I think cool because it was the first time that people were able to do such experiments over non-neighboring nodes in a network, actually, for quantum teleportation. But the rates are quite low, really, right? Like if we want to have this as a fundamental building block of our quantum networks in the future. And so that's why this is a gate sequence here. Sorry, I wanted to say one more thing here. The reason why I'll show you this gate sequence is not like to be like, oh, this is crazy complicated or whatever. It's about that rapid evolution of the field that I want to highlight here. So like, you know, like the first time that people were generating entanglement between NV center was somewhere like 2012, 2013. Now, 10 years later, we're able to run such kind of experiments. And typically, right, when you look at technology evolution, it only accelerates from here. So I'm very hopeful that as a community, maybe not on the NV systematic platform because of limitations, but on some other qubit platform, we can really take that knowledge and bridge it and build much larger network systems in the future. Current research, this is my last slide, and I'm realizing that I'm over time here. So I'm just going to go through this quickly. I think there's kind of 4 main directions I would claim at this point in time. People are interested in a network stack, like kind of the quantum analogon to TCP/IP, if you wish. Of course, like quantum network have a couple of different properties. I think in particular here to highlight entanglement generation is probabilistic and your memory is decoherent. So that means that you might want to think about how to actually do this from the physical qubit layer all the way up to the application layer, where the idea is that at each of those network layers, you only need to have some knowledge about what's going on one layer below you, but not below. So that's, of course, a very important concept as we move on to actually programming applications on a quantum network. Second one is simulations and optimizations, people doing a lot of work in that area. Third one is photonic integration. And multiplexing in particular. I think Bart will probably talk about this, I hope, quite a bit tomorrow. And then the fourth one is efficient interfaces. So here you can see some of my early fab work in Delft, where we're trying to fab photonic crystal cavities, like all diamond photonic crystal cavities. And then also working on these like optical interfaces where we would have some thin diamond slab that's actually micron thin, but still thick enough to preserve the optical coherence properties of diamonds. So my research work actually in our group focused mostly on those efficient spin interfaces for next generation systems. I think we're at an exciting moment in time. I want to leave you with that. I think commercial players are entering the space. I put some headlines here. I could have probably found 20 more in the space just over the last 1 or 2 years alone. And I would really like at this point, like if you take one thing away from today, then maybe this picture here. Like how the first classical computer networks looked, and when you look at what our first quantum computer networks labs look like, I think you can see some similarity here. And I think we're really at that moment in time right now, which gets me quite excited personally. Again, thanking the team in Delft here that really did all of that work that I've been talking about before and that I was a part of for many years. Great group of people if you ever get the chance to work with them. And with that, thank you for your attention.
Okay, thanks. I have two quick questions, if I may. So first of all, I'd like to know, you talked about memories and these centers. I'm really curious what are the performance when you say memory, like how long does that mean for you?
Yeah. Sorry, I should have highlighted it. I even had it on a slide, I believe. And I need to look it up because I'm bad with numbers. So these are like the coherence times of the spins in our system. So of the electrons spin and nuclear spin coherence times. Of course, these are like under non-entanglement generation operations. So typically the memory coherence on our system would be on the order, you can do like about 2,000-3,000 entanglement generation attempts before your memory has degraded such that it's not usable to store that spin state information that you wanted to have on it originally. So what that means, right, is that we need to get that efficiency up, if you wish, or work on extending that and making these protocols more robust. And actually, Ronald always has a nice graph, which I didn't bring today, unfortunately, but you can see that both of those lines are going in principle in the right direction for the system. But I think in general that probably really what's needed is my strong belief is to move to other color centers in diamond at this point in time, really to get hopefully even better properties in the future, to combine these efficient optical interfaces. This is where the NV center is lacking, with good spin properties and the carbon register in the surroundings. And that's why I think, for example, the SIV centers that Bart has worked on before are very promising.
Yeah. You introduced the NV centers in terms of the quantum internet, and what would have been different if you had been talking about a quantum computer?
It's a good question. Well, I mean, I think there's different, okay. Maybe I should answer this in a one-on-one conversation to not say something that offends people. Yeah, maybe we'll leave it there. But I mean, I think it also, right, it's like, okay, there's companies that are trying to do that at room temperature, where then the challenge is maybe mostly in fabricating and getting these like dipolar interactions in the right way, getting the NV centers with good spin coherence properties close by to each other. Of course, here that's maybe more for like a distributed network of computers. So I think it a little bit depends also here on the use case that you are interested in. I would say at a high level, and then we can maybe explore it deeper later on.
Check the chat. Somebody can just.
Yeah. Sid Sandra had a question for you on the chat. So this is coming from India.
$1 billion.
Well, I mean, what's the reason? The question is the time frame here, I think. So I think right now, right, like it's probably on the order of $500,000 to $1 million of just hardware. I think in the future, this has to come down drastically. And I think there's a lot of different angles to pursuing this. Yeah, I think I'll leave it there. I think the rest is speculation at this point in time.
Sort of as an outsider, I've thought a bit about quantum computers and quantum sort of algorithms, and I think the ideas of quantum internet, I'm just curious, how tethered are these ideas? Like, suppose quantum computers will never happen because classical computers just get better and better and better and better, and we figure out how to solve things in a way that, you know, just, I don't know. Somebody discovers how to factor things classically, for example, that's still not figured out. So suppose I take out the quantum computers from the discussion entirely. Does that make it easier or harder for quantum internet, quantum distributing intent? I guess what I'm trying to ask, the question I'm grasping towards is that what value is there in distributing entanglement if we're not going to talk about quantum computing?
Well, I mean, I think, okay, there's like a certain security kind of type applications that we know about, right? We were talking about sensing applications this morning and a couple of select ones out of them. I think there's, you know, there's broader applications there as well. I do think actually that like on quantum networks, you could probably look at the history of classical networks and kind of argue that most of the applications of what it's actually going to be used for, we don't even know at this moment in time right now, and we might still develop it. I do think that having quantum, investments in quantum computing should not hurt quantum networks development. There's some kind of interplay there potentially. Yeah, maybe that's where I'll leave it at for this answer.
Let me just ask you one stupid question. Okay, the Alice Bob Charlie setup that you showed,
yeah.
Was the Bob node in effect a quantum repeater?
So that's a good question, and let's not get maybe into this. But when does a quantum repeater repeat? I think there's different definitions. In principle, of course, that's the fundamental operation that you would have on a quantum repeater. But here you're not beating like any channel bounds or like getting any higher rate. In that sense, it's not a quantum repeater, even though it uses the operation as you correctly identified that you would in a future quantum repeater. And then these, I've written whole papers about like these definitions and things, but like I think you really get in the weeds. And I also think that the whole community maybe hasn't, one specific definition on quantum repeaters at this point in time, I would say.
Yes, no.
So in the beginning, you mentioned, sorry for my voice. In the beginning, you mentioned using the magnetic field of the Earth to create a better navigating system. So I'm just not sure how this is an application to quantum sensing. And also I wanted to know if you started already with a project or it's just an idea and
yeah, so the two applications that I was talking about in the sandbox part of my talk. And again, right, like the quantum networks, that's my previous PhD work. That's not work that we're actively working on at Sandbox at this moment in time. So on I think your question was twofold, like are we actually working on these applications? And what is its relation with quantum? Exactly. So like on the two ones that I showed you earlier today, we each have dedicated teams for those applications. We have actually contracts also with larger organizations working towards those things. As I said in the MCG case, we have a blog post on our sandboxaq.com and then blogs. You can see a lot of like activity there as well, where we announced that we are trialing our system in a hospital environment. And then on the QNAF section, we're also like actively working on that system. Now, on your second question, and okay, what's a quantum sensor? I think I'm still looking for the best definition here in my mind still. I feel like there's also a couple one there. I mean, we're not using any kind of entanglement phenomena or something, right? Like to be clear, for example, one platform that we've publicly stated that we're working with is actually NV centers in Diamond. You can think of why I ended up with Sandbox. But here, right, like we're kind of at the very other extreme of the spectrum. So in these experiments here, which makes it also cool for me because you get to learn some new stuff. So like here you would use like a single NV sensor in Diamond versus in our sensing experiments, you would like use millions of NV sensors in Diamond in that crystal. So it's really like to boost signal strength, right? So it's really the opposite end of the spectrum, I would say then.
Yes.
On one of your slides, you're talking about the readout fidelity of the states, and then you presented two results. One is what the state is that the MSE equals to 0, and the other one is that 1. But you have two different main particle numbers. One is like 0.47, and the other one is.
Let's see. Oh, so these are like.
So
the mean for this, a mean occupation number is like the mean number of photons detected in a certain time window if I'm in the MS1 state or in the MS equals 0 state. Actually, our system is such that in principle, because of the way that we do readout, right, and how the readout is on the MS equals 0 transition, you actually get a higher fidelity readout result in the 0 state than in the 1 state. And for this teleportation experiment, for example, there are a couple of like major things that enable that experiment. One of them is to actually do a repetitive readout where you do a basis alternation in between. So like if you have a MS equals 1 readout, you wouldn't detect a photon. That gives you a lower fidelity. You would apply a path, make it actually an MS equals 1 spin state, do again a readout, check that now I'm getting a photon, swap it again. And then like after 2 cycles, you get actually a much better readout efficiency. So that's one of the key innovations there. And the other one is on the actual entanglement generation protocol. to apply a pi pulse on the nuclear memory spin as well, and kind of do this like phase evolution tracking of the nuclear spin in real time in computer to be able to feed on it depending on which entanglement generation attempt worked out, because it allows you to extend your memory coherence by factor 10 or so in these experiments. And so we're kind of like starting to approach regimes, right, where we can use a nuclear spin qubits even under many entanglement generations, and electron spin qubits under many entanglement generation attempts.
So we had another thing on the chat.
Yeah, they can't hear the question.
Oh, they can't hear the questions. Okay, so I should repeat the question, I guess. Okay.
Sorry, I didn't know that. Otherwise, I would have repeated the questions.
Okay.
So these are all measurements on single defect.
Yes, everything that I presented you here is a single defect, unless, of course, like we are like entangling, then, well, you could two to tango, I guess, in that case, at least.
Okay, any further questions? I guess if not, let's thank the speaker again. And so now we'll have we'll pick up again at 1:30. Lunch is over there. I saw it come in. And please eat lunch and discuss. That's the idea behind this. Okay, thank you.
No, I don't have your.
I think that was called the means of we should get IT.
Should I, Mark?
The lights are here.
Unless you have our email address. I know he wasn't written, but I don't.
Yeah.
About this setup, I'm the next speaker.
No.
Okay.
I mean, you have time.
I have lots of time, so
You should
we can maybe reconvene later.
turn off the camera.
Testing the sound. Can we have a sound check on the remote people? Great. All right. Thanks for letting us know. You go to a convenience store, you know that you'll want to perform a computation in the future of a certain size, and that's the device that you'll purchase. This device is generic. It doesn't have a computation encoded in it. It's in it itself. Okay, so did I write this? Yes, the device is generic. It's untrusted. So when you purchase this, it's really a box. It has buttons. You can give it input, get output. But there's no understanding and no trust on what's going on inside. It could be just really anything. So this is the model of device independence, if you've heard of that. And then what does the box do? We're not saying exactly what it's going to do when we have protocols to do it. In the honest case, it's going to return the outcome of a single constant size measurement from a predetermined logarithmic sized output. So it's relatively small. It's not like as large as the actual computation that you'll be doing, for instance. And then you go home. In the future, you'll have a computation in mind that you want to do. And see, at your desk here, you're interacting with two things: a quantum cloud that's remote, as well as the device that you've purchased. Okay, so you will ask a question to the cloud and also ask a question to the device. The cloud is going to answer. This is all classical interaction. The cloud's going to answer classically, and the device is also going to answer classically. The properties that we want is that the computation is verifiable, meaning that the client then knows that the outcome is correct. The next thing, it's called relativistic. And what this means is that, as I mentioned, there's one message going out to the cloud and one message going to the off-the-shelf device. You get an answer, and then you're done. So the reason why it's called relativistic is that this is a model that's particularly feasible to implement, and because we want isolation between the device and the cloud. Okay, so from this client's point of view, it's important that there's no communication between the remote device and the, between the cloud and the off-the-shelf device. And this can be enforced in a relativistic protocol using distance and the limitation on the speed of light, hence called relativistic, namely the client sends a question in different directions, gets the answers, and based on the timing of the answers can be convinced that there was an isolation condition there between these two parties. So that's relativistic. So this is a desirable feature of delegation protocols. Plus, there's an extra feature that we add. It's called zero knowledge. Zero knowledge, and I'll get more into this towards the end of the talk and describing intuitively a lot more what this means. Zero knowledge is the counterintuitive property that it's possible to be convinced of something without learning anything about how that proof came about, how it was created, or other related properties of that proof. So this zero knowledge property is particularly relevant in the cybersecurity world, especially for quantum cloud computers. So this would mean when the protocol is zero knowledge, that the client learns the outcome, doesn't learn anything else. In particular, can't reverse engineer how that answer came about. So for proprietary information for quantum clouds, this is can be very desirable. Yes. Okay, so the device receives an input and returns an output. Okay, maybe I will change the order next time. So you give it the input, which is of a logarithmic size, and the size. What's the parameter? You'll ask me. The parameter is the input size of the computation that they want to perform. So logarithmic in that input size of the computation is the number of the length of the question that the client asks the one time okay, I did some other work on OTPs, one-time programs, but this is OTS for off-the-shelf device. Okay, and then returns, and then the outcome is like maybe a light bulb shines or something. but not just one light bulb, it's actually the outcome of a constant size measurement.
If it's predetermined, why do you need the input?
Okay, so predetermined is the meaning that generic. Okay, it kind of goes with this one, means that it doesn't depend on the computation that they're trying to do. Yes, there's more than one. There's actually a polynomial number, 2 to the log n. Yeah.
The device, is it connected to the cloud or can it be connected?
Okay, so the way that we're going to implement it is that the device will be entangled with the cloud. In the honest behavior, in order to be able to become convinced and do the computation, there will be EPR pairs between the two. Of course, quantum, what does it mean connection? That's the part that there is. What there is not, and what the client needs to be convinced of, otherwise this won't be verifiable, is that there's no communication between these while the protocol is executed. Yes, I would like to encourage further questions to understand this concept, so that your mind is at ease and when we continue. So, any more questions about this model, etc. Yeah.
You're trying to demonstrate entanglement without the possibility of communication. Like what is the device achieving?
Thanks to this setup, which is the combination of having the device and access to the quantum cloud. The thing that we're achieving is delegation of quantum computation, meaning that the client has any arbitrary quantum circuit that they want to run, and then they can get the outcome of that circuit.
Mm-hmm. And trust that it wasn't done like in a classical way or something.
Interestingly enough, I'm not sure that I can actually say anything that it was quantum, because that's not the statement. The statement says correct. Okay, so the answer is correct. Yeah, we haven't looked at that dimension. Maybe you can be convinced that there's entanglement, stuff like that. Yeah. Another question? Okay, so now let's go into how did delegated quantum computation start, and how do we, and this kind of, you're kind of bringing in ideas and tools, and that's how we finally get to this off-the-shelf device. There's messages in the chat. I just want to double check. I think we've seen these. Yeah. Okay. And the story starts in 2001 with the measure-based model for quantum computation by Rausendorf and Briegel, which is an alternative to the circuit-based model of quantum computation. And it's universal. You can encode any computation, quantum computation that you want to do into this. Okay, into this thing that's called a cluster state. Each node here is a qubit in the plus state. Each edge is a 2-qubit interaction, actually controls Z gate. And when you want to go and do a computation, first of all, you do these computational basis measurements, which kind of remove qubits in the cluster state. And then there is a sequence of layered measurements. You'll measure an entire layer of qubits in the XY plane, get a measurement outcome, and that's going to determine the angle of measurement for the next layer of qubits. It's called feed forward, and you keep on measuring these qubits until the end adaptively, and at the end, this is the outcome of the quantum computation. So it's a really different way to think about computations, and that's where we bringing together different collaborators, which I'll mention in a moment. We realized that we could have some cryptographic application thanks to this way of thinking of how we could do quantum computations. The result is called blind quantum computing, and it's a way for a classical client to delegate a computation using the quantum server. And the client needs to prepare single qubits, which are actually rotated versions of these qubits in the cluster state. send them over to the server, and the server is going to operate on them in a way that's analogous to the computation you just saw. And then there's going to be classical interaction between the two parties. Basically, Alice is going to be driving the computation. She knows what the underlying computation should be. And but giving instructions to Bob that are generic in the sense that because he doesn't know the original preparation of the qubits, he can't interpret those commands. All he can do is follow them. And then Alice can, getting the outcome here, she can reinterpret it based on all the secrets that she knows and basically decrypt it and know the outcome of the computation. So that is this blind quantum computation. And Mark was asking me about the origins a little bit of this. And yes, we were working on this together. And here's the proof in 2000. We got together in 2009, so slightly after with Elham and Joe. This was in Edinburgh. And we were discussing the experiment that that followed. So in Vienna, there was an optical experiment based on this blind quantum computing. So that was in the measurement-based model for quantum computation, and it was really pivotal in understanding, as I mentioned, different ways of computation and how you could add secrecy to that, etc. Let me emphasize it in the blind quantum computation. What's secret is the computation that's being performed. You may have noticed that I all of a sudden switched to secrecy of computation, whereas originally I presented it as verifiability of computation. There are really close links between the two. We'll see that shortly.
So, excuse
Yeah.
me, so when you say that computation is secret, so if I think of a normal circuit, like
Yes.
some quantum circuit, so you're executing something like the quantum circuit, but the person who's executing it doesn't know what all the gates are. Okay.
Correct. For those who are listening remotely, the observation is that what does it mean for the secrecy of a circuit? Like I might call it blind, I might call it secret, I might call it private. Is that the client knows a circuit that they want to execute, the server is helping run that circuit, but the server doesn't know anything about what is the actual circuit that's underlying. So maybe you have a proprietary algorithm for your favorite problem. You want to run it on a quantum cloud. You don't want the quantum cloud to know what the algorithm is. Yeah. So using this insight from the measurement-based model, it's possible to rephrase and do the same functionality, same functionality basically. There's some small differences in terms of efficiency in the circuit model. So maybe some of you are more familiar with the circuit model. There is a way to also think about private quantum computations in the circuit model. So that's what I did in follow-up work that I'm going to tell you about. And there was also an accompanying experiment. In the circuit model, it looks a little bit different. And then you can see a little bit more of the cryptography. So you may have heard about the classical one-time pad. That's a way to encrypt a message. A plaintext X is encrypted as X or a K, where K is a random, that's what this notation means, is a random uniform key. So this is the one-time pad for a single bit. And then we have security because the ciphertext itself is uniformly random based on the randomness of the key. There's a quantum analog of this? Yeah, question. Oh yeah, no problem. Oh, maybe this one here? Yeah. Oh yeah, so the question is, is this different from fully homomorphic encryption? And of course it's quantum. So yeah, like we were coming up with blind quantum computing almost at the same time as Craig Gentry at IBM was coming up with fully homomorphic encryption. I didn't know about it. I was just not really in that loop. So like a few months after that, I was like, oh, look at this thing. It looks similar. What's the differences, etc. So fully homomorphic encryption, for those who don't know about it, is to compute on encrypted data. So it sounds, oh, It sounds like it's the same. The difference here is that the client chooses the computation. So in FHE, it's the server that chooses what they want to do. So we don't need to plan for any possible computation in our ciphertext. And the next thing is that it's going to be interactive. So we're okay with interaction, and that's a big difference in fully homomorphic encryption. There's a quantum analog of the one-time pad, which is the quantum one-time pad. And here we need 2 bits of key in order to encrypt a single qubit. And those bits are going to determine a random poly. So based on A and B, which are random bits, either 0 or 1, we'll be applying one of 4 possibilities here in terms of polys. You know, if both A and B are 0, it's the identity. Otherwise, you might have just X, just Z, or both of them. And then we have a similar argument. If we don't know the key, the ciphertext is a maximally mixed state. So that shows that it's completely independent of the plain text. Okay, why am I talking about this one-time pad thing? The idea is that for quantum computing on encrypted data, we're going to have a method to apply quantum gates on data that's encrypted, on quantum data that's encrypted. So you fix a universal gate set. Here we'll use the TP control not Hadamard's pretty standard gate set. And the high level idea is that we'll start by encrypting the input with the keys. Here we'll have 6 keys. This is an example of a 3-qubit circuit. And then each time that there's a gate in the target circuit, we'll have a gadget, which is a subroutine that's going to emulate applying that gate on the encrypted data. So there's, from the point of view of the client, there are encryption keys on these wires coming in. And we have a gadget, and I'll tell you more about the gadget shortly, such that after the gadget, we have a key update that the client can compute based on the gadget. And the idea is that if we were to stop the computation, like say stop it at this time step and decrypt with these keys on these wires, we would get the state had we run the regular computation on the regular input without encryptions. Okay, so we keep on going this way. I have all these gadgets. And we'll eventually get the output. And now you've noticed that I'm talking about computing on encrypted data. So there's like 3 things we talked about: verifiable, quantum computation, hiding the circuit, and now I'm hiding the data. If you have a way to hide the data, you can also hide the circuit. And that's via a very common technique called the universal circuit. So you would tell the server, I want to do this circuit. And that circuit is so generic that based on the input, you can tailor it to perform any computation of a size. So what this protocol does leak is an upper bound on the size of the quantum computation, and that's unavoidable. Okay, so just some slides that tell you what are these gadgets. If there's a single qubit preparation, you simply prepare it and set the key to 0. If you want to do a single qubit measurement, so the input wire coming in is encrypted with an X to the A, Z to the B. The measurement is in the computational basis. So basically you can forget about that Z component of the key, and the output will be a classical wire. That's what these 2 wires symbolize, encrypted with only the key A. So now we found the classical one-time pad out of the quantum one-time pad. So that's good. And then some other gates in our universal gate set are called Clifford group gates. These are the normalizer of the poly group. In other words, Cliffords map polys to polys. And that's really useful because our key is a poly. So if you apply a Clifford gate to something that's encrypted with a poly, then by definition, all you have to do is to update the poly based on the gate that you applied. So specifically, the X gate doesn't do anything to the keys, the Z gate either. The Hadamard swaps between the X and B part of the key. C0 is slightly more complicated, and the P is as described here. So for universal quantum computation, we know that we need a non-Clifford group gate. We do the T gate, also called the pi/8 gate. And it doesn't have that nice structure. If you tried to simply apply the T gate on something that's encrypted, then you actually get this possible P correction based on A, which is part of the X key. So we can't use the same trick. I mean, you can maybe use it once, but then you have this P thing and you no longer have the nice structure of your key. So the main idea is that we're going to use interaction in the protocol, and the client is going to get the server to correct this error, so this P error, without the server finding out whether or not there was a P error. Because of course, whether or not there was a P error is information related to the key, and that would be bad. That would violate our computing unencrypted data. This gadget looks like this. Details are not important for this talk. We have the server who has an incoming wire. It actually does the T gate, and then we go into this situation where this client sends an auxiliary qubit with the plus that has some rotation based on 2 extra secrets, Y and D, that are uniform to start with. And then the server does this control NOT, does a measurement on the top wire, sends the measurement result to the client, and does this conditional P based on this X classical bit that the client has computed and sent over. So all of this together combines to apply a P gate without the server knowing whether or not they're applying a P gate. And then there's a key update, which is the following. Notice that this one has a multiplication. The other ones only had XORs. For me, this is kind of like the T gate is kind of like the multiplication gate for classical cryptography and fully homomorphic encryption. It's the hard gate, and the key update also reflects that with a multiplication.
And the server sees
Yes.
the classical bits.
The server sees the classical bits. Yeah, the server will see X, actually they receive it, and C, which is sent back. These red is only from the client's point of view. So the client keeps updating those, and at the end can decrypt using that red information. Yeah, then my next slide is about verifiability. So are there any further questions about the privacy, hiding the circuit, hiding the computation, computing unencrypted data, etc.? And I realize I don't have a clock or anything. I have half an hour. Thank you. So let's talk about verifiability. Verifiability. Okay, so now we want to be convinced that the outcome is correct. This is related to that question at the beginning. I said, okay, you perform a remote quantum computation. How do you know the outcome is correct? And then as another illustrative example, let's think about the person who's doing an experiment, the person who's building a quantum computer. This is my cartoon picture of the scientific method. I don't know, maybe you can, some of you can give me some updates here. This is maybe what I learned in high school. So we make a hypothesis based on the hypothesis of prediction, and then we'll verify the prediction experimentally. This totally breaks down quantumly. If you're building a large-scale quantum computer, we won't be able to do this step of prediction. So that's because the predictions of quantum mechanics are, as far as we know, exponentially difficult to compute. So we need this an alternative to the predict and verify paradigm. And this was brought up in particular by Aharonov and Vazirani in 2012. So how are we going to verify a quantum computation? Some people might say, oh, I'll test small parts. These ones are small enough, I can manage these. And when I build the larger computer, I will keep on assuming that those small parts work as I did test them. That introduces an extra assumption. It introduces the assumption that when you build, when you put small pieces together, they keep on working the way that you expect them to work. So if we would say we don't want to do that, we can maybe test computations that are easy to verify. So for instance, factoring. So that's of course one of the big use cases of quantum computers. And that one has a particularity that if you receive a solution to the factoring problem, you can efficiently multiply. Multiplication is easy, factoring is considered to be difficult. That does not encompass the hardest quantum problems, which are the BQP complete problems, such as approximating the Jones polynomial, and certainly many others. For our purposes, we'll consider that evaluating a quantum circuit is a generic hard problem, a generic hardest problem for quantum computers, because you can actually encode any computation in a quantum circuit. Let me emphasize that we're talking about, there's still like polynomial time quantum computers here. And we're in the regime of polynomial time quantum computer, polynomial time classical verifier. When you think about a proof, probably the first thing that comes to mind is a static proof, meaning that I ask you a question, you return an answer, that's the proof. The answer is the proof, I verify that proof. And, you know, I'll do whatever I can on my side to verify. For instance, if it's factoring, we'll ask integer here, and then the prover returns P and Q, claiming that those are a prime decomposition, and I can verify. So P and Q are the proof. I can verify that the proof is valid by checking this multiplication. The thing is, we've known in theoretical computer science for a long time that there is way more to verification than static proofs. And that kind of came out of this question, can we verify more than NP? NP is this type of situation where there's an efficient verification. MA is the probabilistic version, which is just as good for practical purposes. So can we verify more than MA? And I have a story to illustrate the power of interaction for verification. Okay, so this is kind of like maybe an oral exam or something where the verifier is asking questions to the prover. And it turns out you can verify a lot more. And note that I'm not asking the verifier to become more powerful. I'm not asking the verifier to be able to predict the answer, but I'm going to have this interactive version that improves the capacity of the verifier to check larger classes of problems. So I first saw this example in a talk by Dorit Aharonov, but I'm not sure who to attribute it to. Please let me know if you have any further information. So the story is of, let's say it's a mother, and she is sitting under a tree with her child, and the child says, I can count the number of leaves on this tree. And the mother's like, okay, that's great. How many leaves? And the child is like 20,826. Okay, so the mother's like, okay, interesting. How do I know that's true? You know, I just like no idea. The mother cannot verify herself. She will assume that she doesn't have that power. So she comes up with some interesting idea. She's like, okay, child, puts the child in a safe space, turns the child around so that they can't see and can't hear, and kind of puts them a little bit further away. The mother climbs up the tree and removes some leaves. Okay, so say she removes 10 leaves and then burns them to destroy the evidence. And then okay, a child comes back. Okay, kid, you know, how many leaves are there now? Oh, okay, 20,000, 200, I don't know how much I said, 20,216, which is original number minus 10. Oh, wow, okay, the mother's like, oh, that increases my confidence that this child is telling the truth, that there's really some interesting capacity here to count the number of leaves. And notice that what the mother has done is really simple. It has nothing to do with counting leaves. It has to do with like adding an extra challenge. She knows the answer, child doesn't know the answer, and kind of the child is proving it in some way. I mean, the analogy breaks down if you really push it to the limits, but that really shows that this interactive process has increased the verification power of the mother. So in theoretical computer science, this is called IP equals P space, which was a big result in the early 90s. So everything that can be computed in polynomial space, which is considered very large, can be proven in an interactive process between a polynomial time verifier and an unbounded prover in this case. So that's our inspiration. We're going to interact with the quantum device, whether you're the experimenter, give challenges to the device that are include some secrets that the device doesn't know. If you're a client and you're trying to interact with a remote quantum computer, trying to know that the outcome is correct, you're going to give challenges, some of which you know the answer. Other challenges you don't know the answer, and those are the useful ones for you. And use that power of interaction to be able to do things that you couldn't do non-interactively. Okay, so if you're thinking of yourself as the experimenter, in this case, for this type of interaction that we're going to do, we will assume that the experimenter can verify and characterize very simple quantum systems, predict the output of trivial quantum computations. Say you do the identity on the input 0. The input is 0, the output is 0, okay? Pretty trivial quantum computation. You can predict the outcome of that even as a classical verifier. And you can also interact. So send qubits. So verify and characterize simple quantum systems will be actually sending qubits, single qubits to the quantum computer, very similar to the model of blind quantum computation that we had at the beginning. But here we're adding verification, let me emphasize. So the result is that we can bootstrap somehow this small quantum capability of sending single qubits and the interaction implies verification of large quantum systems. And here's where the cryptography comes in. So far, for the verification, well, maybe you got a little bit of sense of cryptography, like the leaves, removing the leaves and burning them was like hiding a secret or something. Here, this blindness or the computing on encrypted data is really important. What we're going to do is we're going to get the quantum server to do computations. Some of them are test runs. They have outcomes that are easy to predict. And other runs are the actual computation. These ones have outcomes that are that we don't know how to predict. And the point is that the prover or the server will not be able to tell if it's being tested or if it's doing the computation. So it's got to be honest on the tests. It's got to be honest on the tests. It can't tell if it's being tested or computation. Therefore, it's got to be honest on the computation. And therefore, we can trust the outcome of the computation. That's a high level idea. Okay, so we'll analyze the behavior, and either the prover is benign, meaning that it's almost, it's basically honest, maybe doing something strange, but that strangeness is not changing the output of the computation, or non-benign, meaning that it's actually actively deviating, and this is going to be detected, and the client will reject, saying this computer is not doing what it should be doing. And the way to do this is by doing more gadgets. So we had the gadget for the quantum computing on encrypted data, where the T-gate gadget, which was applying a T-gate on encrypted data. Now we're going to have more sophisticated gadgets, and we're going to have different ones based on what type of run we're doing. Are we doing computation? We have different tests. One of them is called the X test. The other one is called the Z test. And if you look at the dashed line and on the top of it, from the point of view of the server, they are doing exactly the same thing. So they're doing these circuit elements. The client is working in the background to do something that relates to whether they're testing or doing the computation. And then the outcome is also encrypted in this way. The point is that in this X test run, we expect this deterministic outcome, C equals A XOR D. The details are not important, where this comes from, et cetera. Meaning that the client needs to see A XOR D as answer. If it's not, the client will reject. So what we have right now, so far at least, is a client with a classical computer and some quantum power, namely preparing these single qubits. I didn't tell you the details of what these are. They're basically rotated qubits, tensor product of rotated qubits. And the qubits are sent over to the large scale quantum computer. And now we have classical interaction, and we've managed to get verifiability. Now, what if there's no quantum power for the client? Everything we've talked about so far had the client preparing auxiliary qubits, sending them over. It seems, okay, if you want to argue for quantum networks, that's great. Okay, every client needs to be able to send qubits to the quantum cloud. That way we need quantum nodes everywhere. That could be difficult. So what if you want to have clients that are classical on a conventional network interacting with a quantum cloud? Can we still get privacy? Can we still get verifiability? It's a completely different question. I mean, we can use what techniques from what we know so far, but this is really a change of model. Okay, so could we have a classical verifier? There are some answers that are known. So actually, the breakthrough result of Urmila Mahadev in 2018 is that we can use computational assumptions. So we'll assume some, turns out to be learning with errors, or lattice-based computational assumptions. We'll assume that those assumptions cannot be broken even by quantum computers. And then that allows a classical client to interact with a quantum computer and being able to delegate both private and verifiable quantum computations. What if you're not willing to make computational assumptions? Okay, so maybe your trust in post-quantum cryptography is not that strong, or maybe you just want to see what are the possibilities and limitations here. Well, there's one solution by Reichert, Unger, and Vazirani, which is we'll have a classical client. It'll be interacting classically. Now we have two quantum servers, two quantum clouds. The quantum clouds are need to be isolated, so we need to be able to ask them independent questions, and they can't coordinate while the protocol is executing. They can't coordinate together, and also the protocol has these servers being entangled. So taking advantage of that entanglement, Reichert, Unger, and Vazirani showed that we can actually become confident that a computation is performed correctly. And this is a really fundamental result that is very much a topic of current interest. It's called rigidity of non-local games. When we had the setup here where there's two servers and we're asking classical questions, that's a lot like Bell inequality setup. It is Bell inequality setup for those of you who know about this. If you think about SHSH game, a magic square game, Bell inequalities, you're like querying and asking for measurement outcomes for quantum devices. You don't know anything about the quantum devices. If you see some Bell inequality violation, you can conclude that there was some sort of entanglement or quantum mechanical phenomena. So we push that to the limit. We look at the parameters of a specific game. So there's questions and answers here for Alice and Bob. And then rigidity is the statement that if the verifier observes close to optimal winning probability over multiple iterations of this protocol, then the verifier can conclude very strong mathematical statements about the behavior of Alice and Bob, namely that they must be up to some, let me just say, they must essentially be performing the optimal strategy of the game. Okay, so like say you're thinking about CHSH, okay, you know that with one EPR pair and doing such and such measurements, then they can win optimally with probability cosquare pi/8. Then if you play the game multiple times, see the statistics, and it's close to the optimal probability, then you can conclude that actually they were sharing n EPR pairs, where n is the number of runs you did, and that they were performing these measurements that correspond to the optimal strategy for a CHSH. So this is another way to kind of enforce honest behavior. Previously, we had tests and computation runs. This is the rigidity way to enforce honest behavior that's controlled by a fully classical verifier. Okay, so then the verifier can use the knowledge of this optimal strategy to deduce honest behavior on challenges that are related to quantum computations. So we'll use this intermingling idea, and the servers don't know whether they're playing the game, whether they're doing the computation. If they're playing the game, they have to win optimally, otherwise the verifier is going to reject. Winning optimally implies some sort of rigidity statement, and that transfers to the computation, and then we know that the computation is performed correctly. So that was like that was the spirit of RUV, Reichardt Unger Vezirani. And that's been brought into many areas of delegated quantum computation, including this one here that I want to mention, that there's two provers. And what they did is they took the quantum computing unencrypted data that we saw previously, added some non-local game, used the rigidity of the non-local game to conclude that this is being performed correctly. And that gives you delegated quantum computation in this model, classical client, two isolated quantum servers. Okay, now we want to make these protocols more and more feasible, simple. We want to understand them. We want to make them closer to something that we could maybe demonstrate. Right, okay, so because there's many limitations in the original protocol. For instance, what Alex Grillo did in this work was to make the protocol relativistic. At the very beginning, we talked about relativistic protocols, meaning that the client sends a single question, gets a single answer, and that's it. Okay, so the interaction, there is interaction, yet it's minimal. And he managed to do that. And he managed to kind of like overcome this barrier of the T gates that usually require communication, back and forth communication to fix some poly, to return to some of the poly paradigm for encryption, and to remove some possibly erroneous gate. So instead, he looked at some other way to verify a quantum computation, which comes from the circuit to Hamiltonian construction, which is a way to kind of encode a quantum computation into a quantum state. So you encode many steps of a quantum computation into a quantum state. It's also, people know about it like this clock state type of construction. So now we reduce the verification to the estimation of the ground energy of a local Hamiltonian, and verifying that is called the energy test. So there's a quantum state that is basically the proof. And what they do is that if Alice is going to teleport the quantum state to Bob in the honest situation, and then the verifier is going to get Bob to do some measurement for them. And that measurement is the test, the energy test that you would do on the local Hamiltonian to verify it. The problem is, of course, there's no reason for the verifier to trust that Alice and Bob are doing this. So we'll add some rigidity. So what Grillo did was came up with a non-local game that perfectly fits with the computation task that they want to do, and showed the rigidity of that. Okay, I think we're okay. Now I can tell you of how all of that has been brought into the off-the-shelf device. Off-the-shelf device is kind of like two provers, Alice and Bob, but we'll say that the second prover, Bob, is particularly small and generic. It doesn't even depend, it doesn't depend on the problem that you're trying to solve. Okay, so that's why I put scissors. So our challenge here in this work was to find a non-local game, prove a rigidity statement, and show how that could be combined with a computation thing like verifying a Hamiltonian to and make all those pieces fit together and be able to conclude that the outcome of the computation is correct. So that's what we did. And the technical techniques, actually, I would highly recommend for those who want to hear more. There's a second version of this talk, which would be the mathematical techniques that are used. And Arthur is my colleague at the University of Ottawa. Yuming is a talented graduate student in Waterloo, and both of them would be fantastic, I think, to tell you a lot more about these details. So we developed this new self-test for low-weight polybraiding test, which satisfies the requirements that we need for Bob in order to be able to have an off-the-shelf device. Ooh, okay. And then I promised to tell you about zero knowledge. Do I still have time?
is fine.
Oh, perfect. Okay. I promised to tell you about zero knowledge. Remember there was this cybersecurity thing? I said, oh, we can even add this property that the client learns the outcome and nothing else. This is super counterintuitive. Like if somebody gives you a proof, like usually you want to check the steps of the proof, right? Like how could you just say, yeah, it's correct without learning anything about the steps of the proof? And here's my second little analogy for today. It's Where's Waldo? And in Where's Waldo, for those of you who don't know it, and I know Waldo has different names in different countries, the idea is that you need to find many characters, including the Waldo character. I just freaked out there. Including the Waldo character on a page. Actually, this is a subset of the page. It's usually much larger and much more difficult. Okay, so can I prove to you that I know where's Waldo without telling you where is Waldo? Without you being able to actually learn where Waldo is on the sheet of paper. And I didn't come prepared today because I have the demonstration. Here's a demonstration on the screen. I will take a large piece of paper. I think it has to be twice, maybe 3 times the size of the actual Waldo page. And I will punch a little hole in that large piece of paper. And then I'll align the book so that you can see through the hole that there's a Waldo. But I'll make the hole small enough so that you can't see the context around it. Okay, so you will be convinced that I know where's Waldo. I've shown you. You don't learn anything about it, and particularly you can convince somebody else about it. You couldn't find him yourself. Okay, and this is my little illustration of it. It's pretty. The hole would have to be a little bit smaller. So now you get information, and yeah. Anyways, that's the idea. So in principle, there's ways to get zero knowledge, and this is something that's studied in depth. For quantum zero knowledge, that's kind of, it started maybe, I don't know, 5 to 10 years ago. Actually, maybe more like 15 years ago with some initial work, but now we have more and more coming out. And there's this really cool technique called simulatable codes. Comes from Grillo, Slofstra, and UN. And it's a code, think about it like an error correcting code or something, that if you encode data into that code, it kind of spreads out. Okay, it definitely spreads out. It spreads out so much that if you look at the reduced density on a small number of qubits, any subset of qubits, say so like 3 qubits, and you look at that reduced density matrix, that is efficiently simulatable. So maybe the original message that you've encoded into that code is difficult to come across. Once you put it into that encoding system, if you look at small subsystems, each one of those is really easy to compute. So how could that be, right? Locally, these things are really easy to compute. Globally, it's really difficult to compute. Classically, this intuition completely breaks down. If I tell you that there's a large string and I give you substrings of it, and all those substrings are easy to compute, then you can put them all together side by side, get the large string. So therefore, the large thing is also easy to compute. Quantumly, it's very different. And we can really see that phenomena in simulatable codes. Quantumly, we don't know how small pieces of a proof may be entangled in order to create the larger proof. If you've seen other talks of mine, I really have this fixation with apples. And I really kind of think of apples as quantum states. So this kind of comes from this analogy that if you have apple slices, and so these are like quantum states, it could be difficult to put them together to get the whole apple. Okay, so the simulatable codes are what we're going to use also to add to this off-the-shelf device model. We'll use the low-weight polybraiding test that we talked about previously, which was a rigidity thing that's compatible with off-the-shelf. We'll use the simulatable codes to get zero knowledge. And then that gives us the result that I promised at the beginning, delegation of quantum computation with this off-the-shelf model. It's relativistic and it's zero knowledge. Thanks a lot. Just a second, actually. Benefit of the
Oh, sure, yes.
yeah.
Yeah, I'm loud.
No, the benefit of the
Oh, right.
the remote, yeah.
Just-
the Zoom
Okay.
Yeah,
Well, thanks for the great talk. You might have mentioned it, but I might have missed it, so my apologies. But when you do delegation, secure delegation of computation, you also have to have efficient provability, right? So did you assume I think there was a slide that you assume that your prover is a polynomial time quantum?
Oh, okay, thank you. So I didn't emphasize very much the model for the prover. For today's purposes, I was always thinking about the prover being quantum polynomial time in the sense of a quantum cloud. If you read this paper, it's all about actually QMA and other classes, but they're all very much related. So yeah, let's think about the more concrete situation of the quantum cloud has polynomial time quantum computations. Yeah.
Thank you.
So you said that the one of the, like, I think in response to like a question very beginning, you said that the key is to have entangled pairs, right, between kind of the off-the-shelf device and the prover. And so how many of those pairs do you need? And does the size of the computation that you can delegate, does it depend on how many entangled pairs you have?
Yeah, thanks for the question. The number of entangled pairs will be directly linked to the size of the Hamiltonian that is the proof of the computation. Hence, yes, the size of the device as well as the size of the number of EPR pairs will be exactly actually because we basically Alice teleports it to Bob. So n EPR pairs for a ground state with n qubits. Yeah.
I have a casual question about the low weight Pauli braiding test. So just the word braiding makes me think of topological quantum computing, and I'm wondering if there's any relationship at all.
Oh, there must be in the concept. So it's a test that has like different polys, and you'll like swap them around, and then have different questions based on how many you've swapped or something like that. So I don't know, that's the extent probably to which it's related to what did you say, topology or?
Yeah, so
yeah,
so maybe.
Yeah. Yeah, often actually like you come up with a protocol that works. I mean, it just works. So you're happy. You're like, okay, I'll prove that, I'm done. But there's certainly generalizations that could be like maybe more elegant. Yeah.
Well, let me just add, this is probably kind of obvious, but okay, so you've got the non-local games. So if you're doing the CHSH game, so if they can show that they can do it with the sort of maximum entanglement from a maximally entangled state, then you know that they've got the state. This sounds an awful lot like the sort of quantum crypto with untrusted devices. So I assume there's a relation.
Okay, yeah. If you take quantum crypto as meaning accomplishing tasks in the presence of an adversary, then this is quantum crypto, where we're doing device independent delegation of quantum computations. Okay, because we're not trusting anything about what the devices are doing. We've also seen things like device independent quantum key distribution, and those also use I mean, I think that's the only technique we have right now is rigidity. So they also use rigidity to gain confidence on what the devices are doing, and then be able to conclude that there's a shared secret key.
Okay.
Yeah.
Okay, any other questions? Okay, if not, let's thank the speaker again. Yeah.
So you just arrived.
Yeah.
Yeah. So let's hope that this is all gonna, you know what to do at this point, right? Okay.
This morning. So it's actually nice to meet you.
Yeah, nice
It's
to meet you.
actually
Great.
a Zoom call
Okay.
that you'll share your screen on.
Okay, sounds good. Let's do it. So where do I go for the,
So I don't.
oh, the Zoom link? Maybe I can just do
Oh.
this.
Oh, okay, sure.
Is that gonna work?
I think that's simple enough.
Ooh, the method.
Okay, good.
And I keep my audio on, right?
Yes. Mhm.
No, no, the audio is gonna come from that computer.
No, no, but I keep my, remember how like, oh, it's-
Yeah,
oh, I-
it's that one.
okay, how about my video off?
Uh,
Do
uh,
we have enough cameras?
Okay.
Are you on Zoom yourself?
Yeah, yeah. I'll
Okay,
just-
good.
Yeah, yeah.
I'll just share the entire desktop
Yeah, we're getting better,
Yeah,
better.
and I'll just do this and I minimize.
So people wandered out, you were calling back in?
Yeah.
Let's see.
They're picking up extra coffee.
Yeah,
let's
wait 5 minutes, let people get a coffee or something.
Are you here both days or just today?
I'm here for like most of tomorrow, I think, yeah.
Okay.
Yeah. Yeah.
I'm-
And actually, I don't have that many slides, so it's good, actually. It's fine. We can start a little later and ask a lot of questions. We're good. Okay.
We have, this workshop's not packed with talks, so.
Right. And is it all working well? I mean, I
It's-
guess this is unmuted and
Yeah. no,
slides are
I think we're good.
clicking.
Yeah,
Okay.
yeah.
That was fast. Okay, cool.
One of the best.
Thanks for having me. And sorry for all the trouble with the travel. It's always like with NIST, it's always like that. You know, I'm sorry. I'm sorry. I know I got some emails that I think you had to participate in. I'm sorry. I'm sorry.
No, whenever you have to deal
Yeah, I'm
with the
sorry.
government, it's.
I'm sorry.
I think it's best, yeah, I kind of like just was grain that information, because like keeping track, so what exactly was the issue that you cannot be reimbursed?
Well,
You can't be reimbursed, yeah.
yes, and then also like if reimbursed, like you can't reimburse me, you have to reimburse them, and they wouldn't and it wouldn't let me,
That was for the train.
and they wouldn't let me travel in the cell actually, because like that's business class, yeah. But if you buy it from me, it's okay.
Okay.
No, that makes sense. No, don't they have, at least with, I remember, what was it, maybe within a set, there are some restrictions, like they need to book tickets or something like this, there's a government agency or something. I remember dealing with this one.
I remember it's been a while since I've been on an NSF. We actually met on an NSF.
Yes, I remember,
A
yes,
long
yes.
time ago.
Right.
I haven't dealt with them in quite a bit, so I forget whether they bought the tickets or.
Yeah, anyway, thank you, sorry, thank you, sorry.
This is a minor, well, maybe for Mark, this is a major.
I'm sorry. Water, so.
No, I mean, actually, John handled a lot of it, so.
Thank you to John as well, who was here.
Right, no, I'm gonna have to run off at 3:30 unfortunately,
Yeah, no problem.
or I'll be here all day, that's why.
Mhm.
So that's where you sit, like in this building?
It's complicated, no, I've been sabbatical at Flatiron. Chair and my home campus is.
I really want to set up my entire apartment like this.
So you
I
never.
want to set up my entire
I always
apartment.
have
like
a-
this.
Oh, it's
Like-
high speed and-
So I think I
We're not-
used to be.
you always have
this would be
blackboards
my
in your
place to do kind of
That's
like
true.
science business, so I would basically just would run.
So
seminars and
You
everything.
give the girls
But
a
for
full set of
undergraduate,
non-foundation and sort of here.
we
Start in the
most part.
We leave all the important books on the low bookshelf.
Okay.
And so I would be 2 days there and 3 days here.
Well, anyway,
So
nice
far,
to
they've
meet you.
been
No,
calling
I
to
just
Calvin and Hobbes. but We're gonna move them to Landau. and Lipton.
Okay.
No, it used to be really great because people were very happy.
Get them to
to come
something.
and,
Exactly.
You know, for a day, like I remember when all the couple.
Yeah, just by sheer coincidence, the apartment that we moved into, the previous tenants painted an entire wall in the kitchen with that
I
chocolate
know you're
paint.
very busy.
Oh, really?
Which has just
We'd
been
love to have you.
great. They just leave a bowl of chalk in the kitchen and they just.
Great on the train there and back, so he like, so in 2 weeks. Yeah, I have a free Friday.
On normal short boards nowadays.
I had like, I think.
No,
all of us
it's
started-
not as good as actually.
It's not as
displayed.
good as that.
It cracks and it flakes and it gets old. It's.
So it used to be really kind of like my.
Technically it works.
Basically, just letting people know that I'm here and then ask them and.
Well, JFK is kind of far. It's not like a 10 minute walk.
Train that comes here, like it's a half hour, you can make it into a half hour. No, but if you have like a 6 hour layover.
I see.
That sort of thing. She gets to draw her giant robots and everything.
Maybe unusually advised. No, but it was also one.
And I'm basically looking at what's long. And then.
Yeah, there's what is that? One-
No, I.
What's that?
Neither of you is flat.
Flat Earth is about- Oh, Lauren is entirely flat. Oh, yeah.
I sort of like it right down here, and I guess I'm wrong. It's been a while since I've seen her.
here, to give you a sense of it,
Okay,
this
yeah.
is.
It'll
this
be
is the
nice
first side
to
of the
visit
family.
again. There'll be some nice parallels.
Oh, that's where it comes from.
Sorry.
Okay, yeah.
All right.
And they've got a brother too. I mean, it's across the board.
I'm sorry.
Sorry, yeah, it's been quite a while since I've seen Lawrence.
This big. No, their hair is exactly the same.
Scandinavian descent or something?
German, I think.
Side note, I think
I've got all the Scandinavian blood, but all the people on my side of the family are.
family reasons.
Right here.
Again, we get any people someday.
Yeah, so yeah, definitely, schools there are.
Yeah.
Pretty good.
When Nora was born, she was born with, she has bright blue eyes.
But-
And I was talking to my mother, and I was like, I have,
Weather's different in a bad way.
I mean, of course, Lauren has blue eyes as well, so she definitely has the genes, but. I didn't realize that I had blue eyed genes in my family. My mother's like, you know that I have blue eyes. I'm like, oh, well, I mean, of course, you do.
Before I go.
Very exciting.
Great stuff.
Sort of missed it. I've been going.
Yes, like, there's one of the sweets that we're writing a couple more papers, but we're still writing.
Yeah, I mean, I think people have that, I don't.
Yeah, I took a trade. It's very convenient, but it's still like trade.
So at least one of the talks tomorrow will not be, because one of the speakers. Yep, he said it. The kind of permissions for you have to be under. So much pain. Okay, we won't break that.
Is there an office where you can remote?
I know guy at IBM, you Nick Rowan, who's been kind enough to.
See right there.
And yeah, pandemic, I was like, it will be, I'm not sure.
Yeah, what's your feeling with companies and all the proprietary information? Record it, sure. Yeah. There's not much more. Listen. Here's everything I've ever felt. Sorry. Right. Joints. If you're remotely hung around. I would be employed. Yeah.
One of the things that talks
And then it'll be well, it's.
how much of that is just website?
Like there was what we did before, like first try. Before in the days, you
Yeah. Again, well, I've been- Since he's supporting me, we couldn't reimburse him for his travel. We would have to reimburse. He wanted to take it, he could. But it's and then the flying train taking that. Like, I didn't read the paper, but I haven't. Like, I don't know, it's like, yeah, that's like, one thing. If the referee says it's wrong, then it's like, well, let's say, classification wrong. It's super hard. It's just fun, but it's kind of like interaction. We government. You can also talk about the marginal side. Oh, I think it might have had to be this.
Double. Maybe. Saying, you know, the thing that I don't know is how to reduce the data.
We can even consider is not something. If we're going to leave them out, yes, how much it's there. It's not clear whether absolutely. Okay, anyway, okay, so let's go ahead and start the last talk of the day. The talk is given by Alexei Gorshkov from basically NIST. And so this will be our second talk on quantum sensor networks. So this will be, I guess, mainly a theory talk. The first one was combination of theory and experiment. So
Thank you so much. Yeah, thank you so much, Mark, for inviting, and thanks to all of you for being here. And exactly as Mark said, this talk will have some nice synergies with Jeshan's talk earlier this morning. And I actually don't have a huge number of slides. I hope we can make it interactive. Please ask questions. And so I will talk about quantum sensor networks, but maybe I'll remind you what quantum sensors are and why they're useful. So you can say that a quantum sensor is a sensor that uses quantum mechanics in some very fundamental way for sensing. And they're good because on the one hand, they can be very small and they can give rise to high spatial resolution as a result of that. But also because all measurements are fundamentally limited by the laws of quantum mechanics, they can also give rise to a high precision. So here's one example of a sensor. This is a nitrogen vacancy color center in diamond, where you can imagine removing 2 carbon atoms, leaving one side empty and putting a nitrogen instead of the second one. And it turns out that there's an isolated electronic spin here, and the energy levels of this electronic spin, roughly speaking, they can depend on a magnetic field and the temperature. And you will hear more about some other defect centers in diamond, actually in Bart's talk tomorrow. But this nitrogen vacancy center, because it's sensitive to magnetic fields and temperature, it can be used for, say, magnetic imaging of live bacteria or a nanoscale thermometry of live human cells. Let's see, I wonder if I can, there's like stuff here at the bottom that doesn't show it.
Click anywhere on the main screen, by main screen, I mean.
Oh, there. I see.
Click it on there.
I clicked right away. Yeah. Now I click again.
Click anywhere.
Or maybe click the chat.
No,
Oh, maybe, yeah, maybe because the mouse was over the, maybe it'll go away. Okay, let's hope it goes away. Doesn't want to go away. It would be nice for it to.
The previous speaker managed to work.
I see the previous speaker managed to get rid of it somehow.
Click on chat.
Follow other people's advice.
Click on the chat. No, I just want to remove the bottom.
Well, we can click on the chat just because who can see the message? Okay. Maybe it's you.
Me.
No, in your case, it's fine. So what's going on? Oh, wait, are you sharing the screen? Yeah.
Maybe.
I mean, it's not deadly, but all the references will be missing and people will be upset. It's like, why didn't you cite me? It's like, oh, it's all under there. You're all cited. Maybe it's better.
Oh, wait, it happened just now, right? Are you happy now? Okay, there.
But that's kind of small though. right? Well, I mean, I don't know, if people are.
These operations don't commute, you know?
I see. Maybe one, but not a.
Let's try it again.
I see, so it doesn't like doing it at full screen.
Or right now, well, I'm not sure. I'm just trying to replicate what the previous person managed to do. And maybe that's just not.
It should be like,
Sorry.
like a command here in the.
There probably is, but Zoom is kind of not very friendly.
Okay, well, I mean, we'll just deal with this. There's about a one line of stuff that'll be missing.
There we go.
Oh my God, I had to touch it here. I got it, okay. Okay, so this was one example. Another example of a quantum sensor is a Rydberg atom. So a Rydberg atom is an atom with one or more highly excited electrons. And as a result of this high excitation, the negatively charged electron is far from the positively charged core, and there is a large electric dipole moment between them. And this makes the atom very sensitive to electric fields. And so you can use this Rydberg atom for electrometry. So here's one example of a particularly impressive quantum sensor. So this is from the group of Junyi at NIST Boulder. What they do is they trap a bunch of atoms in these kind of one-dimensional pancakes that are oriented vertically, so the gravity is pointing down. And because of general relativity, we know that clocks at different gravitational potentials, they actually click at different rates, and this is known as the gravitational redshift. And now what Junyi and his group managed to do is they managed to measure the gravitational redshift across this 1 millimeter. So each of these atoms are clocks, and they click at slightly different rates because they're at different heights. And they were able to measure the difference in their clicking rates across this 1 millimeter, which is crazy.
You're going to define what it means for an atom to let us.
Well, no, the ticks of the clock. I mean, not clicks, ticks. Just.
So what does that mean? It has some kind of session.
Yeah. They just measured. They basically measured the frequency between two states, and this frequency between the two states, is a ticking of a clock, and so different clocks, tick at different rates depending on the height. But to do this, they need to make this really precise measurement of basically 10 to the minus 20th. Fractional frequency measurement. So, you change a given frequency by 10 to the minus 20th, and that's what allowed them to do this. Very impressive. Okay, so now let me introduce in very basic terms how a simple qubit-based quantum sensor works. This is very, very simple. So suppose we have two states, 0 and 1. And they're just two states in a Hilbert space. And suppose the Hamiltonian is 1/2 theta z, where z is the z Pauli matrix, and theta is the parameter of interest. So you see that the Hamiltonian is diagonal on the z basis. And so theta is just the energy difference between 0 and 1, and we're trying to measure it. So remember, like in those nitrogen vacancy centers, the energy difference was sensitive to the electric field or to temperature, or to magnetic field or to temperature. And then you could measure it. So how do you measure this theta? You prepare a superposition of states 0 and 1. Then you let the state evolve under your Hamiltonian. And then 0 and 1 pick up a relative phase theta t relative to each other. And then to measure this phase, you measure the X Pauli matrix, the X observable. And then you get projected onto states plus and minus with the probabilities given by the overlap of the corresponding state with your wave function. And so you find that you get plus with probability cosine squared theta t over 2. Indeed, at t equal to 0, you start in the state plus, so that makes sense. And then you get p minus with just 1 minus that, which is sine squared theta t over 2. And at this point, we're basically done with our quantum mechanical description. Now we have a random variable that gives a plus with a probability p plus, and that gives minus with probability p minus. And the point is that these probabilities here depend on the parameter theta we're interested in measuring. And so we would like to sample this random variable to try to learn what theta is, what theta is. Now, the general tool to understand how much information is contained in a random variable x about the parameter theta that its distribution depends on is called a Fisher information. And it's defined like this. So it's the sum over the two possible outcomes, plus and minus, and then you take the corresponding probability and multiply it by the derivative squared of the log of that probability. Now, the steeper is the dependence of this probability on theta, the larger is this derivative, and the larger is the information. So that kind of makes sense. The stronger is the dependence, the larger is this Fisher information. And then the famous Cromé-Rao bound tells us that the uncertainty in measuring or extracting this the value of theta from this from these samples is given by 1 over the square root of the Fisher information. Now this is in some sense a kind of a single shot quantity. So you make one measurement and that's your uncertainty. Now in reality, with a single shot, you really don't get much information. You only get 1 bit of information, and it's not very useful. So in reality, what you do is you actually need to run your experiment many times, say m times. Then your Fisher information gets multiplied by m, and then your uncertainty is just 1 over the square root of fm. And in that case, actually, in the limit of large m, you can saturate this inequality. So let's compute now what this quantity is, this Fisher information for our probability distribution. So I'm not going to do the math for you, so you can just plug in this cosine squared here, take the derivative, take the log, take the derivative. And what you find is actually it's very simple. It's just t squared. And then if we plug this in here, we find that the uncertainty in measuring this parameter theta is bounded from below by 1 over t. And this kind of makes sense because if, say, our time is twice as long, then we're sensitive to kind of half the size, of the changes in theta. So a larger time, you're sensitive to smaller changes in theta. Yes, this is yeah, exactly. So all of these are, so this is a very good point. So in reality, you need to be very, very careful. So there are a lot of details, a lot of papers written on that subject that actually you kind of wrap around. They need to worry, that you don't wrap around sort of and don't get confused. These are all very good points. And in fact, if you're careful, then you can sometimes replace this 1 with a pi, kind of for these reasons. So right, yeah, good point. Okay, so right, but I'm gonna kind of forget about all these complications, and I'm just gonna assume that for a single qubit, I can get 1 over t uncertainty. So what we're interested in this workshop is networks. So I want to eventually talk about sensor networks, but for now, let me talk just about n sensors. And suppose all n of these sensors are maybe in the same place and they're coupled to the same parameter theta. And we would like to use these sensors to measure theta. So one way of doing this is to independently use each of these sensors to measure theta. So I prepare a product state, 0 plus 1 on each sensor. And then I just evolve this state under this Hamiltonian. So this is equivalent to just doing n times the same experiment I did in the previous slide. And my uncertainty in the measurement of theta is just reduced by square root of n. So this is just your standard statistical square root of n improvement. And this is called the standard quantum limit. Now, another strategy is to prepare an entangled state, which is the cat-like state 0, 0, 0, 0 plus 1, 1, 1, 1, 1. And what you see is that actually these states are eigenstates of this Hamiltonian, and they're split by n theta. So this means that once you evolve this state under this Hamiltonian, one state picks up a phase of n theta t relative to the other. And we just did this analysis, for a 2-level system, which looked kind of the same, except instead of n theta t, we had theta t here. So by the same token, we now know that the uncertainty for this state is just 1 over nt instead of 1 over t, because we got nt now instead of t in the previous slide. And you might worry that in order to extract this kind of optimal measurement of theta, you need to make a complicated measurement. Well, turns out you don't have to. Turns out you can just measure the x observable on every one of your qubits, and then just multiply the answers. So plus minus 1 and multiply them together. So the reason why you get this improvement of 1 over nt compared to 1 over square root of nt is that in some sense contributions to quantum noise from each sensor conspire to partially cancel each other out. And this is called the Heisenberg limit. And this is the best possible measurement kind of for this problem that's possible in quantum mechanics. Any questions? This is just some very, very basic review. Okay, so now because we're interested in a quantum network, so now let's consider a quantum sensor network, where now each sensor I is coupled to its own parameter theta I. But suppose I'm not interested in learning every single theta. Suppose I'm only interested in measuring one particular linear combination of these fields. So suppose this is the desired linear combination. So these alpha are the coefficients that I prescribe, and thetas I don't know, so I want to learn one linear combination. So here's a cartoon of what this setup would look like. You imagine, say, a cell, and inside the cell, you have 4 sensors. Each sensor has a field that's unknown. Could be an electromagnetic field, a temperature. And it also has a weight, alpha I, and this weight we pick. So for simplicity, I will assume that these weights are real, but it's easy to generalize to complex weights as well. So why would you care then about measuring the specific linear combination? Well, in some sense, you're targeting a particular spatial profile of the desired signal. So maybe you're interested in a Fourier mode or a spherical harmonic. Maybe you're interested in some question or some spatial signal profile that's sort of concentrated on this side of the cell or kind of in the periphery compared to the sensor, compared to the center. And so by adjusting these coefficients alpha, you kind of change the type of question you're asking. So let's see, what we can do here. Let's suppose first that we don't use entanglement. And we want to learn this linear combination. So then without entanglement, we just individually measure every theta 1, every theta I, and then we just compute Q. So then our measurement of each theta I has the uncertainty 1 over t. That was from the second slide of my talk. And then I just compute Q. And then the uncertainty, the computation of Q is just given by this sort of weighted sum of the variances, and then I take the square root. So I plug in a 1 over t here, and I get the square root of the sum of alpha squared. So this is what I get without entanglement. Now with entanglement, we had to do some analysis. This was actually a while ago, 2018 or even before. We have many parameters. So now instead of this Fisher information, we use something called the Fisher information matrix. And there is a corresponding Cramer-Rao bound for this multi-parameter setting. Then we use some results by others. And we arrive at the following bound. So this is with entanglement. So instead of the square root of the sum over alpha squared, turns out the lower bound that we get with entanglement is just the size of the largest alpha I. And you see that this is always less than or equal than that. So you can potentially do better because the size of the largest one is always smaller than the square root of the sum of the squares of all of them. So according to this bound, and I haven't even told you whether we can sort of saturate or not, turns out we can, but according to this bound, the uncertainty is given just by the single site with the largest alpha. So let's try to see whether these formulas make sense. First, let's suppose that I want to use this network to measure only theta1. So I choose alpha1 equal to 1, and I choose the other alphas to be 0. And then I plug this in here, and I get a 1 over t. And I plug again alpha1. Alpha1 is the largest one. I plug it here. I get again 1 over t. Good. So if I just want to measure theta1, there shouldn't really be any difference between the entangled strategy and the unentangled strategy, because I'm just measuring a single theta. I'm just going to use that one qubit to do it. The other qubits are useless. So here's another extreme case. Suppose I want to measure the average of the thetas. So I take all the alphas to be equal to 1 over n. So then I plug this in here, and I get 1 over n squared, but there are n of them. So I get 1 over n, and then square root 1 over t root n. And this is exactly the standard quantum limit that I derived maybe in the third slide or something like that. On the other hand, if I plug in a kind of 1 over n in here, which is the largest alpha, I get 1 over nt. And this is actually the Heisenberg limit in some sense that I derived, that I showed earlier. However, what this bound allows us to do, it allows us basically to fully interpolate between these two scenarios. So one where we're interested in just one of them, the other one is where we're interested in the average. But this formula sort of explains what happens for all possible choices of this alpha. And the question that you should be asking is, okay, well, that's a bound. I mean, maybe maybe that's not a very good bound. Maybe you can get a tighter bound. So is there a protocol that saturates the bound? So yes, it turns out there is a protocol, and it's very simple. So I assume that my alphas are real, but let me furthermore assume that they're all non-negative, and they order them in this order from the smallest to the largest. Now, the assumption of them being non-negative is not a very restrictive one, because I can apply some pulses, some pi pulses, to change z into minus z, which effectively changes sort of theta to minus theta, which is equivalent to changing alpha to minus alpha. So it's not a big deal, but let's assume they're all non-negative. And furthermore, let me assume that the largest alpha is 1. And this is, again, not very restrictive, because I can just divide my quantity of interest by the amplitude of the largest alpha. And then the largest alpha becomes 1. So let's assume this. So the protocol starts with the same cat-like state. And then what I want to do in some sense is I want to evolve the qubit under this Hamiltonian for a time that's proportional to its alpha. And then it will sort of pick up a phase that's proportional to the alpha as well. So here's what I mean by this. So on the x-axis, I have the time. I assume I have 3 qubits, 1, 2, and 3. And here I will write the Hamiltonian times 2. So for the first length interval of time, alpha 1t, I want to evolve under the full Hamiltonian. For the second time interval from alpha 1t to alpha 2t, I want to decouple qubit 1 from its parameter, and I want the qubit 1 to not change its state in some sense. And for the third interval of time, I only want qubit 3 to be coupled to its parameter. And finally, here I have a sort of alpha 3t, but alpha 3 is 1, so it's just t. So how can I achieve this? How can I achieve this sort of decoupling? There are at least 2 ways of doing this. One is I can imagine that I have some other states in my sensor that are not coupled to the parameter, or maybe halfway through this red interval, I can apply a pi pulse that changes z1 to minus z1, and I just echo away the this term theta 1 z1 over this red time interval. So now what happens then is that the first qubit picks up phase theta 1 for time alpha 1t. The second qubit picks up phase theta 2 for time alpha 2t. And the last qubit picks up its phase theta 3 for the full time t. So I put them all together, and this is exactly the linear combination q that I was interested in times t. So very simple. So this is exactly the q that I was interested in. And based on the second slide that of the talk, I know that I can measure it with the uncertainty 1/t just by measuring this parity. And since my largest alpha here was 1, this exactly saturates the bound. So something you might be wondering about is it's kind of surprising this is optimal because during these red time intervals, the corresponding qubits don't do anything. So this first qubit is kind of lazy. It's not active during this red time interval. The second qubit is not active here. So how can this be optimal? So this time seems to be sort of wasted. And to emphasize this question, let me suggest a different protocol that kind of seems naively to be better. Here's an alternative protocol on 2 qubits. So we start with the state 0, 0 plus 1, 1. As before, we first evolve under the full Hamiltonian for time alpha 1t. So both qubits pick up the corresponding phase. But now, instead of just turning off the coupling of the first qubit to the field theta 1, I'm going to disentangle the 2 qubits. So I'm going to apply basically a sort of a controlled NOT gate. And then again, so the controlled NOT gate disentangles the first qubit from the second qubit. And then I'm going to also rotate the disentangled first qubit in the state 0 plus 1. So now the accumulated phase stays on the second qubit. And now I again evolve under the full Hamiltonian. So the remaining time is alpha 2 minus alpha 1t, where alpha 2 is 1. So now I've gotten my signal Q right here, but I've got now more information compared to the protocol in the previous slide. So it looks like it's basically the same as the first protocol, plus some extra information about theta 1. And this is probably better. I should be able to somehow use this extra information about theta 1 to learn what Q is. But the point is that without any prior information about what the quantity Q is, knowing theta 1 even exactly doesn't actually help. So to illustrate this, let's play a game. So suppose I'm thinking of 2 real numbers, say A and B, and I'm asking you to guess their sum. And now I'm going to give you a hint. B is equal to 13. But if I, didn't tell you anything about what A and B were with no prior information, this extra information is useless. You're just as clueless about what it is with or without the knowledge of that 13. Now you could say that, well, okay, fine, but in real situations, you always have prior information. So it's still surprising that the protocol is optimal. Well, the reason it is optimal is that we're asking questions sort of asymptotically in the large time limit. And in that case, all the prior information becomes sort of not important. It's sort of related to, I guess, Vadim's question that we're really interested in the really kind of asymptotic questions where we really know already pretty well what our quantity is, and we're just trying to measure it better and better. So that's why this prior information doesn't really matter, and that's why even knowing theta 1 exactly doesn't help, and that's why these better protocols don't help. So any questions? Okay. So yeah, so this was again it's pretty old. So back then, it was sort of we were excited about this. It was the best measurement allowed by quantum mechanics, and in some sense, this protocol was secure in the sense that as long as we control at least one of the nodes, eavesdroppers have no information about the measurement result because we're preparing those GHZ states, and as long as you control one of the nodes, nobody will really learn the phase. It's also important to point out that you can really use the same trick to optimally combine data from different types of sensors. So you could, for example, theta 1 could be sensitive to the electric field, theta 2 to a magnetic field, and theta 3 to temperature. So now let's try to make it more interesting. So so far we tried to measure linear combination, But now suppose we want to generalize and measure any desired analytic function Q of theta 1 and theta n. For example, it could be a theta 1 times theta 2. So it turns out the protocol in this case is very, very simple. What you do is you first use unentangled measurements to estimate the values of individual theta I. And I call these estimates theta I tilde. And you spend a negligible fraction of your total time making these estimates. So after you've made these estimates, you take your analytic function you want to measure, and you just linearize it around your estimates. So you just do Taylor expansion to first order in these corrections, theta I minus theta I tilde. And then you just ignore the higher order terms. And then the protocol is just to notice now that this approximate quantity is now linear in these theta I that we don't know, and we can use the linear combination protocol that I described. And then what we showed in this paper is that if you choose cleverly this negligible fraction of time, you can make sure that these higher order terms are in fact negligible. And so this protocol becomes asymptotically optimal for measuring any desired analytic function. So let's try to make it more interesting. So far, we took our parameters theta, and we wanted to measure some function of these thetas. But now let's generalize. Let's suppose that we have a vector of k unknown parameters, theta 1 through theta k, but suppose they don't couple directly to our sensors zi. Instead, let's suppose there are some other functions fi that depend on these thetas, and these functions fi couple to the to our qubits. And we still want to measure some function q of these thetas. So the difference now is that thetas don't couple directly, it's some functions of them that couple to the qubits. And these functions are given, and this q is given. And so what can we do? So first, we assume that we actually have enough sensors to, in principle, learn what this entire vector of thetas is. So forget about entanglement. Suppose I spend a lot of time to measure f1, f2, etc. And then what I assume is I have enough sensors to then basically compute from the knowledge of all of these f's what the thetas are. So suppose that's the assumption. I have enough sensors. But then assuming that I have enough sensors, what is the optimal protocol for measuring this one particular linear combination, one particular function q? Right. So this is basically the assumption is that the number of these sensors is greater or equal to the number of the unknowns. And the problem is that we can't really directly use our earlier results, because if there are many sensors, then there are infinitely many ways to express this function of interest q in terms of these parameters, in terms of these functions fi. And so I don't really know how to apply our earlier results. But we found actually the optimal protocol in this case. And in some sense, I mean, this protocol is really the optimization of all possible ways of expressing q in terms of these fi's. But I'm not going to go into details what the protocol is. Instead, I'll try to motivate, why is this useful? So here's an example for why it's useful. Suppose you have a box. And suppose inside this box, you have some unit electric charges, which I will draw as these green circles. And suppose I have two of them. So there's one of them at position R1, and another one is at position R2. And I don't know these positions. So R1 has the x and y coordinate of charge 1, and R2 has the x and y coordinates of charge 2. So I have a total of 4 unknowns, so x and y coordinates of these two electric charges. And now let's suppose that I can sense the z component of the electric field at sensor I, and sensors will be these red circles. Suppose I have one sensor right here that measures the z component of the electric field, another sensor here, and 3 more sensors right there. So if I knew the positions of these charges, I could compute the electric field at this position, at this position, at this position, at this position, at that position. And these are exactly the functions f1 through f5. And now suppose I want to know what is the Z component of electric field at this position star. But the problem is that, this box is closed. I cannot really put a sensor there. So the sensors are sitting outside. And furthermore, I cannot see inside the box, and I don't know actually where R1 and R2 are. So I somehow want to optimally use these sensors that sit outside the box to learn one specific quantity, this field at this point, inside the box. So maybe as something more useful than this picture, you can think of sensors sitting, outside a volcano, and these sensors are measuring the gravitational potential. And as the magma inside the volcano, rises slowly, you want to know that it's rising, and you want to sort of say, "Hey guys, there's going to be a volcano eruption soon." So in addition to say measuring like a specific point, you can also, for example, say that Q is some integral over some field of the field over some region. So here I consider electric charges. I mean, it could also be a nuclear spins producing a magnetic field, or as an example that I just mentioned, it could be just some mass producing a gravitational potential, or many other examples. So any questions so far? Yeah.
I know what, if I know the physics of the problem, can I just pull out a Jackson and compute that, or?
Right, you can do that. You can do this. You can do this, and this is exactly what these functions are: F1, F2, F3, F4, F5. But I don't know what R1 and R2 are.
Right, but if you know, oh, I see. The idea is that I don't know the field everywhere in space. I know the field in 5.
You know the field. You know the field only here, and furthermore, you don't know it. You want to measure it, and you want to measure it as quickly as possible. And one thing you could do is you could actually measure the field here, 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 and there. You measure it, take a long time, no entanglement. Then from this, you can compute what R1 and R2 are, and then you know everything. But this might take a long time. Suppose you don't want to know R1 and R2, you only want to know what is the field, at this point, and you want to learn it as quickly as possible. And then, there's the optimal strategy. You entangle these sensors in a very clever way. So good question. Thank you. More questions? Okay. Right. So let's now forget about this complicated problem. Let's suppose we're again back at the original problem where we have the parameters theta I that are coupled to qubits through this Pauli matrix Zi, and we want to learn the linear combination. So far, the protocols that I showed you, as long as all the alphas are non-zero, all of them start with this n qubit cat state. And this state is a kind of very entangled in the sense that all n qubits are entangled. I mean, it's not very entangled in the sense of sort of volume law and area law. It's actually not very entangled in that sense, but still all the qubits are entangled. Such entangled states are hard to create, and they decohere fast. So is there a way of somehow reducing the amount of entanglement? So can we achieve the same optimal measurement by entangling fewer qubits? And the key to answering this question turns out, well, the answer is actually yes sometimes. And the key is to divide our total time into fractions, PM, that sum to 1. And then I coherently switch between different sort of superpositions of states psi n as psi n prime for each time fraction. And as we switch, this phase theta keeps accumulating, and eventually it accumulates to be something proportional to Q. If you remember kind of the original protocol, I was kind of hiding my qubits, or I was applying pi pulses. So, I mean, this is sort of similar to it, but a generalization. And using this trick, what we find is that if a particular condition is satisfied, a condition depending on some integer k, then we can achieve optimal measurement with at most k-partite entanglement. So let's try to kind of digest this. Yes?
So what are psi n and psi n prime?
Yeah, so you can think of them as two orthogonal states. And this is some bit string, basically 0, 1, 1, 0, 0, 1, and this is another bit string, and they're orthogonal. Well, they're different bit strings. And I'm not really saying what they are because I need to cleverly choose them. But if I want my entanglement to be low, then these bit strings need to agree on many of the bits, and then I can factor it out. Great question, thanks. Right. So for now, I'm assuming everything is perfect, and then we can sort of separately analyze, and in some of the papers, we considered that, but it's a very important question. So I can address maybe partially now. So or maybe fine, let me address it, and then I'm sort of in the middle of explaining this. I'll come back to it. It's okay. That's a good question. So in general, the answer to the question of decoherence is that as long as if the stuff you're measuring is basically not changing, so if it's just a fixed parameter, and right, if it's not changing, then it turns out using these entangled strategies in general is not particularly helpful because and also using these less entangled strategies is also not helpful. Because this state, it allows you to measure things faster, but it also decoheres faster, and it happens to be a wash. So the situations where these entangled strategies, all of them that I talk in this talk, they're useful is if the thing you're measuring is sort of short-lived. Maybe your signal is changing, so you want to measure it as quickly as possible. So this is the general answer. There are also, I'll mention in the Outlook, there's a lot of work on error correction in sensing. Which allows you to do sort of better than the naive strategy. But yes, it's a good question. More questions? So I didn't really explain this yet, so don't ask questions about this just yet. Okay, so there's a particular condition here that allows me to achieve optimal measurement with at most k-partet entanglement. So what is this formula here? So this is the sum of the amplitudes of the alpha I, and this is the largest alpha I. So let's try to understand what this means. Suppose I want to measure only a single theta 1. So then my alpha 1 is 1 and all the other alphas are 0. I plug this here, I get 1 on the left-hand side and also get 1 on the right-hand side. So I can achieve this inequality with k equal to 1. So it means that one partet entanglement, so no entanglement is needed, which makes sense. If I want to measure just theta 1, I just use that qubit and measure theta 1, and other qubits are useless. Now, another extreme case is, suppose I want to measure the average of these thetas. So I choose alpha I to be 1 over n for all I. So I plug this on the left, I get n times 1 over n, so I get 1. And k is equal to k times 1 over n. So in order for this to be true, I need k to be n, which again makes sense. If I want to measure the average, I really need to entangle all of them. This is how I get this Heisenberg limit. And so what this inequality really tells you is that kind of the more unbalanced the sum is, kind of the more things are concentrated on certain qubits than on other qubits, the less entanglement you need to optimally measure this quantity. Questions? So when should I end? I know we started like 20 minutes late or something. 50, I don't have that much actually left.
Well, you're certainly another 10 minutes.
Okay, sounds good. Cool. More questions? Okay, so let's now generalize it a little bit further. Suppose you want to measure multiple functions. So before we considered measuring a single linear combination, but now suppose you want to measure several linear combinations given by this alpha 1 superscript through alpha m superscript. And the goal is to minimize the sum of the variances of the corresponding m estimators for these Qs. So here are some example strategies that you can imagine using. One strategy, you forget about entanglement. You measure theta 1 through theta n, and then just compute these Qs. So another strategy you can imagine is you break your time into m fractions, and then spend the first fraction of time optimally measuring Q1, the second time fraction optimally measuring Q2, and then the last time fraction optimally measuring QM. And then you optimize over these time fractions. And now a third possible strategy you can imagine is that you sequentially measure other optimally chosen linear combinations, not those linear combinations themselves, and then you compute these linear combinations you're interested in from the ones that you measured. So what we found in this paper is that actually in many cases, especially when the number of sensors is much larger than the number of function you're interested in, then this third strategy, which is kind of the non-obvious one, works best. So briefly now, the applications of all of these sensor networks can be either at small scale or kind of interest this workshop on large scale. So on small intermediate scales, you can imagine, say, studying the structure of some protein where the nuclear spins in your nuclei produce magnetic fields, and you're measuring these magnetic fields to learn the structure of the protein. Or you can study some processes in cells or humans. And applications are in chemistry, biology, and medicine for measuring magnetic fields, electric fields, and temperature. Now, on larger scales, you can imagine entangling these sensors, either over the scale of the globe, or perhaps over the scale of a volcano. And then you can imagine application in geodesy and geophysics, or perhaps predict quickly volcano eruptions or earthquakes. And again, you would be measuring magnetic fields, electric fields, temperature, gravity, etc. So to summarize, we found often optimal entanglement-based protocols for measuring one or more properties of spatially varying fields. Now, there's lots more work to be done. You can ask the question of how to optimally place the sensors. We already discussed that there's a lot of work in sensing now on error-corrected sensing. So you kind of try to correct your errors without really using your optimal scaling. And sometimes it's possible, sometimes not. So, so far in the talk, I always consider the case that each parameter was coupled to a generator, in that case, Z1 through Zn, and they were all commuting. But this is not always the case. You can imagine that your parameter theta1 is coupled to the X Pauli matrix, and your parameter theta2 is coupled to the Y Pauli matrix on the same qubit. This is a much harder problem, and there's a lot of work on that as well. So far, I assumed my fields are time independent. It's interesting to consider measurements of time dependent or stochastic fields. You can allow for the movement of sensors during the measurement. And again, some things can be done better that way. Kind of related to Anne's talk, suppose you want to do your quantum sensing in such a way that maybe there's a server who owns your sensors, and you want to learn something from that server without really divulging to the server, what your question is, or possibly even without having the server learn what the answer is. And there are some papers on that already. And finally, here I make the connection to Jashan's talk in the morning. Really, I focused on qubits, but really a lot of the same ideas they apply to photons or phonons as sensors, where you can imagine that you have a photonic or phononic, in general, bosonic modes that couple to your unknowns either like this through the number operator, or like that through a quadrature operator. And maybe let me just show 2 slides on this, and then I'll conclude. So this is an example of, and again, this closely now connects to Jashan's talk. Here's an example where entangled optical photons were used as sensors. So you imagine here that theta1, theta2, theta3, and theta4 are some unknown phase shifts, and you're interested in this paper in measuring the average of these phase shifts. And what you do is you create some clever non-classical state of light that allows you to do it optimally. And now this is actually Jashan's work, where optical photons are now replaced with radio frequency photons. And these phase shifts are now replaced with displacements in phase space. And again, you kind of create some non-classical state of light, in this case, squeeze state, squeeze vacuum, followed by some linear circuit, and then you do this measurement of some function of these alpha 1 through alpha m, you do it optimally. So with this, let me thank a lot of people who contributed to many of these papers that I mentioned, and some funding agencies, some past and current group members, and thank you for your attention.
Do we have any questions? So, yeah, let's turn this microphone on. Oh, anyway. Okay. Yeah, what did I do? Oh, it is on. Oh, okay. All right. Okay, any questions on this? Yes.
Yeah, great talk, Alexi. I do have a question about the quantum state. So here, you assume you always use this GHZ state, but each sensor would actually experience different time to construct that linear function. But could you also maybe construct a different state so that all the sensors would spend exactly the same amount of time on sensing?
Right. So even in fact, maybe I need to. I guess they heard because you used the microphone, so I don't need to repeat the question. So even in the original paper, we construct a few other states where instead of basically doing sort of something active on your state during the measurement, you just construct your state, which somehow encodes your question. So we do discuss this case. I mean, yes, there are some slightly uglier states that do that, although I think the way we constructed it there is it maybe only holds kind of only for like short times, or I guess for small signals rather. But yes, you can definitely do it. Good question.
Thanks for your talk. I was wondering if you could maybe shed some light on some of those biological examples that you said about like small systems and realizing some of those ideas experimentally, how you see that evolve over time, when it might become relevant for what kind of questions. I'd be curious to learn about that.
Yeah, good question. So in general, as far as using quantum sensors, in general, without entanglement, I guess people already do it in biological systems. So I mentioned, some work actually from a while ago. It's basically when say Harvard people and other people in Germany, started working on these nitrogen vacancy centers, in diamond, they realized they can make good magnetometers. And they wrote papers where they measured. I showed these pictures where they measured. Say magnetic fields inside a cell or temperature inside a cell by considering a small diamond nanocrystal. Inside that crystal is the NV center, and this NV center, is sensitive to temperature and magnetic field. So without entanglement, it's definitely useful. And there's a company that they started. I'm sure there are other companies too, but I just know of the one at Harvard. It's called Diamond Technologies or something like this, where that's exactly the idea, to use these diamond sensors for kind of biomedical applications. Now, if your question is when will these entangled protocols be useful, it's not obvious that they will be useful. First, if you can put more and more sensors in there, I don't know, maybe inside your diamond nanocrystal, you can put more and more of these NV centers, as long as they don't sort of interfere with each other. If you don't put them too close to each other, your sensing becomes better and better the more of these sensors you have. So, you just get this standard quantum limit 1/² event improvement. So when these entangled strategies become useful is when you've exhausted all of your kind of entanglement free strategies. I don't know, you've saturated your system with qubits. Maybe people are making clocks these days, and they put so many atoms that if they put more atoms, they're colliding with each other. And so just like last month, I think there were 3 different papers where they show how in atomic clocks they can prepare entangled states of the atoms to make better clocks. But for these biological applications, first, it's difficult to imagine a scenario where you will be exhausting sort of, where you'll be exhausting just the simple unentangle strategy. And second, creating entanglement across the biological samples will be just a big mess. And so, it's hard to imagine that this investment will be worth it, I would guess. But in principle, who knows? Maybe in the future, we'll have everything. Quantum computers and quantum repeaters will work great, and it'll be so easy to entangle two things that it'll be like, oh, why not? Let's get an extra factor of square root of n and entangle these centers or these sensors inside living cells. But I don't see this being a near-term thing.
So I just want to ask, how should minimizing the sum of variance of M estimators would improve the performance?
Right. So I think you're probably asking about I think maybe this one. Yeah, right. Yeah, so this is just so the question is you have this setup, we have these unknown thetas, and you just happen to want to learn not one thing, but say two things, Q1 and Q2. Now, why you would want to do this, that's a separate question. I don't know, maybe you're studying some complicated molecule, and these two parameters, Q1 and Q2, happen to be, I don't know, the angle between two bonds, the angle between two bonds, I don't know, and the angle between like two other bonds. It's some property of two properties of your molecule. Just a random question that you're interested in, two questions. And now the question is, what should be a figure of merit be? Because you're interested in two things. If I'm just interested in one thing, then I know my figure of merit is somehow the uncertainty in how well I know that thing. But if I'm interested in two things, I need to define for myself, how well am I doing? Because I really have an uncertainty of one thing and uncertainty of the other thing, and maybe they're even correlated somehow. So I just chose as my figure of merit, basically, kind of the square root of the sum of the squares of the uncertainties of the individual things. So just the variance of this estimator plus the variance of that estimator square root. So it's just a choice. Maybe you care more about one bond than the other bond, then you will choose a different, a figure of merit. You will kind of weigh one of them more than the other. Good question.
Let me just ask one. Shouldn't I? Okay, we've actually been looking at a somewhat different problem, and I'm kind of wondering if there's any connection between what you've done and what we're doing. We're looking at a network of detectors, some of which interact and some of which don't. And then we're sort of trying to figure out from the quantum state after the interaction, which of the detectors interacted and which didn't. Now, I think the linear functions wouldn't be very good for that because it would sort of generate the same Hamiltonian no matter which ones. But on the other hand, other functions might give information about which ones interacted and which ones didn't. It's just sort of it's kind of unfair dropping a totally new problem on you. But I just want.
No, I really like the question. So maybe maybe what you're asking is a sort of a discrete version of this problem.
Exactly.
Where my thetas are not. I don't really care about learning it. I know that theta is either 1 or 0.
Right.
And I remember actually this question has occurred to me at some point, like what is the discrete version of this? And yeah, but I don't think we've ever looked into it. It's possible that all of these answers, they're all basically asymptotic. But the discrete problem kind of is fundamentally non-asymptotic. I think it's great. So have you solved it? Do you know what the optimal strategy is?
No, bits and pieces. We've solved it in bits and pieces, but we certainly don't have a general answer.
Yeah, it's very interesting. Yeah, it's a great question.
Okay.
Thank you.
Okay. Any other questions? Okay, well, let's thank the speaker again, and let's actually thank all the speakers for a very good day. Okay, please eat something on your way out. I'm going to have to try to figure out what to do with the rest of the food.
I close this Zoom as well?
Yeah, we need to close it and log out.
End, right? Bye, everyone.
Yeah,
And meeting for all?
and meeting for